Nice. Okay. So it's you should click. Yeah, I guess probably here. Yeah. It's my great pleasure to welcome you all for the last day. Of course, we have a lot of fun in the afternoon. So, but usually the fun starts with the scientific part. So the first speaker is a really great pleasure to introduce Vivek. Vivek Bahandri, which is actually a senior scientist here, and Vivek will be talking about the coherency-driven quantum systems.
Thank you. Thank you everyone for showing up this early in the morning. And yeah, my title is like the coherence in periodically driven quantum systems. This work we have been doing from Japan in collaboration with people from University of Rochester and Berkeley. So all the experimental stuff I'll show you would be from UC Berkeley, and all the theory stuff is from University of Rochester in Japan. And yeah, let me start with. So these are the people involved. Most of the work were done by grad students here, Dominic and Erwin. And Dominic works on Fouquet, and Erwin and Khan will be also slides on Kurkat qubits. So those would be from their side, and the experiments were done by the group of Professor Siddiqui. Right. First, let me give you the outline. So this has been the work we have been doing for past 3 years. So we have a lot of things I can show you. We were first interested in this thing about like, can we build? So the journey started from like people from Irfan's group. They asked us if we can understand better how to operate just qubits instead of operating the bare qubits. So we named them Fouquet qubits, and how do you do gates, and how do you operate these Fouquet qubits, and what does decoherence look like in this kind of qubits. So I wouldn't be talking about like gates and readout and all those stuff in this talk, but I would be talking about what does noise characterization or decoherence looks like in this kind of driven systems. So I'll start from simple cases of like monochromatic and bichromatic driving in two-level system. So I'll just consider two-level system and forget about all the rest. Then I'll go into resonant and off-resonant cases, weak and intermediate driving strength, multi-level effects on dephasing and decoherence. And from there on, I will also take a special case of Kurkat qubits off-resonant driving, and we'll look into decoherence in Kurkat qubits. We'll also look into resonant and detuned Kurkat qubits. And at the end, I would like to end my talk with like our current work on noise correlation in this kind of qubits. So we have moved from like single qubit, different regimes, to like now understanding how noise correlates when you go to multiple qubits in your, let's say, quantum processor. So yeah, so why periodically driven systems? So the reason we first were interested in this periodical driven system is because when you drive your qubits, so this is one of the plots I took from our first paper on this topic. So what you can do is that you can engineer interaction between your qubits just by driving the qubits. So suppose you start with like capacitive coupling or XX coupling, let's say, between your two qubits. Now, the only native gate or operation you can do for the qubit would be an XX operation, right? But in order to have like more than just XX operation, what you can do is that you can drive your qubit and engineer a GG interaction. So that's one of the benefits of this thing. The other thing is that by driving, you're like moving your system away from your lab basis. So you're going to a rotated frame. And in the rotated frame, what you can do is that you can do a longitudinal readout compared to a transverse readout. So sigma G can become sigma X, and sigma X can become sigma G. So by rotating the basis, you're like, going from demolition type measurement to non-demolition type measurement. And the other thing is that this is the topic of this talk is like you can introduce dynamical sweet spot by dynamical decoupling, so you can have enhanced lifetime as a function of driving. So let's look further into this topic. And before going into decoherence, I would like to first introduce you what I mean by Fouquet, or what I mean by time periodic system. So let's say I have a static system which has a Hamiltonian H cap, and I have a time-dependent counterpart with H cap t. So in the static system, I have H cap, but like if I have a periodically driven Hamiltonian, I can write H cap t0 plus t as H cap t0. So that's my Hamiltonian to begin with. Now, what happens to your state? So usually the evolution in the static system happens with the eigenvalues of your system, whereas in the time-dependent periodically driven system, you have these Floquet modes and the Floquet quasi-energies that give the evolution of your state. So the evolution of your system, or like the evolution of your state, depends on these epsilon n, which is the quasi-energy, and the QUN, which is quasi-state. And so the general idea is that you start from your lab basis 0 and 1, and then you drive weakly and adiabatically to these rest states U0 and U1, and you want to operate in U0 and U1. So you don't want to operate in the lab basis, but you want to operate in the rest basis. So all the operation and all the decoherence properties I'll be talking about would be in this rest basis. And what is the Floquet Hamiltonian? So Floquet Hamiltonian would be like if I bring back the right-hand side of my Schrödinger equation and I write my Hamiltonian in this way, then I can write this thing as in terms of the Floquet quasi-energies and Floquet quasi modes, and that would be my Floquet Hamiltonian SF. And yeah, so going further, now, what you can do is that since you have this periodic system, you can exploit this periodic symmetry, like in the block theorem in condensed matter. What you can say is that since I am periodic in time, I can write e to the power ik omega t as a ket. And it is like, since it's periodic, k plus 1 will bring you back to k. So now, sorry, if you put it, if it is periodic in time. Now, if I write my, look like an annihilation operator in this manner, I can say f cap k is k minus 1. And if I use this simple relation along with the periodicity of my drive, then I can write my Floquet Hamiltonian in this way. So the expansion, so what I'm saying is that your Floquet Hamiltonian can be expanded on these kets, which are just like periodic operators or periodic states in the sample space. So that's technical stuff, but at the end, what I want to say is that if you have all these things, if you have all this machinery and heavy tools, what people had been doing before was like, okay, so I have all this machinery, Floquet equations and Floquet master, Floquet things, and what I can do is now write the master equation in the Floquet language, and I get this complicated equation, and from this complicated equation, I can extract relaxation and dephasing, and that's what was done in the first paper where they studied this thing in the superconducting qubits at least. So it has been done in other setup, but for superconducting qubits, I think this was one of the first papers. And we did the same. We used the Floquet master equation. But we were looking into this thing in more detail, and we were like, okay, this is just exchange of energy between your system and the environment, right? Although the system is now dressed, it shouldn't be that complicated, because now the exchange happens at the level of dressed state, not at the lab states. So we were like looking into, can we explain this with simple tools instead of going into like looking into master equation and all those things. So actually, we were like, okay, let's use the Hellman-Feynman theorem with this drive. And then using the Hellman-Feynman theorem, we can look into the sensitivity of the quasi-energy gap, how sensitive is the dressed energies are compared to the drive parameters. And we found that at each harmonics, right, for omega k, and even for phase, we can write everything in terms of the expectation value of the drive Hamiltonian. So the zeroth order would give you the DC sensitivity, the real part of the kth harmonic would give you the AC sensitivity, whereas the imaginary part would give you the phase sensitivity. And this is exactly the same. I can take you from here to I can change the language a bit, and I can say, okay, the sensitivity can be written in terms of, so this is the sensitivity of the gap of the Floquet qubit. So now you have to think that these are dressed qubits, not the lab qubit. And in this case, the sensitivity of this dressed qubit depends on this susceptibility chi. And we get this thing from the Hellman-Feynman theorem, and then this susceptibility is a diagonal term given by this thing with its observable. So of course it is a sigma z observable because you are looking into dephasing. And you see you get the expression for gamma phi, and this gamma phi is exactly what you get from the Floquet master equation. So basically you don't need to do all this machinery of Floquet master equation, solve the Floquet master equation, and get the dephasing time. You can just use Hellman-Feynman theorem. And one more thing is that if you use the Floquet, you generally get just a DC sensitivity. Here you get like DC, AC, and all harmonic sensitivity as well as phase sensitivity. So you have more control over like what you want to calculate. Next, how do you do the relaxation? So the relaxation can be done in a similar trick. You can use the Fermi-Golden rule, right? So you can, instead of looking into the bare state, you can look at the dressed state, and you can look into how I can go from one initial state to a final state. So if I go from sigma to sigma prime, right? So if I want to go from one Floquet state to another Floquet state, and that's how you will like interact with your environment, because the environment can give you a photon and you can give the photon back to the environment. And when you capture all these processes, you find the absorption and emission rate, and this gives you the relaxation time. So with just this simple like Fermi-Golden rule and Hellman-Feynman theorem, we were able to like look into like both T1 and T2 time of these Floquet qubits. Now with this machinery and with these tools, we can look into like different things. So first, let me start with like monochromatically and bichromatically driven Floquet qubits. So in order to do that, I take an example of a fluxonium qubit. A fluxonium qubit is like you have a junction, you have a capacitor and an inductor in a parallel, and you thread the loop of the junction and inductor with an external flux phi external. And the Hamiltonian looks like this. And if I put myself in a sweet spot, I wouldn't elaborate on that further, but I can write my two-level Hamiltonian in this way. And I can now do the same thing as before and write my Floquet Hamiltonian, just thinking that I can drive this flux periodically. And if I do that and I calculate the dephasing, the sensitivity of the quasi-energy gap, which is the dephasing time, I find that there are like some reasons where like, you get high insensitivity. So basically you go from lower than 10 to the power minus 4 and further, right? So you have very highly insensitive regions around here. So the DC noise is very small here, and we call them dynamical sweet regions. And the thing is that you get these continuous manifolds of sweet regions, and this does not depend on any calculation of the master equations. So the way we calculated this DC spot was like for each frequency, we calculate the quasi-energy gap and we calculated the gradient. It was very numerically intensive, but using our in-house Julia library, we were able to do that. Now, the other thing we can check now is like we can go beyond this DC sensitivity using our calculations. We can look into AC sensitivity, right? We can look at different harmonics. So first harmonic, second harmonic here. And we find one interesting thing, like at the first harmonic, I have a curve that starts at 1/2, but then if I go to second harmonic, this disappears. And we are still trying to understand this thing. This was just, I think we observed this thing a week back, but I have some explanation of why this dynamical sweet region appear, why you have this DC insensitivity and AC insensitivity of your qubit, but that will come a little bit later. First, I would like to show you something on the bichromatic driving. So what you can think of like, okay, now I have DC insensitivity and I have AC insensitivity. Can I have both, right? With monochromatic driving, you can't do both. So we looked into like, okay, let's try doing bichromatic driving. Let's drive two tones. So I have one tone, which is N1, the other tone is N2 omega. I determine the strength of my drive through this mixing angle nu. And I use 1/f noise and dielectric thermal noise, along with like these parameters for my fluxonium, the same setup again. And I find, so I would like to follow you the black curves in this plot, and the black curves gives me a DC sensitivity. And you see that the DC sensitivity, the DC insensitivity is super broad for like the resonant drive. So if you follow the dashed black curve, it has a very broad insensitive region. Whereas the resonant curve has a very high AC sensitivity. That's what I was saying before. Monochromatic driving has only one good thing. Either you get a big DC insensitivity or AC insensitivity, but you can't have both of the worlds. So the same thing with off resonant, you have the small AC sensitivity, whereas the DC has a very narrow place where you have to fix. Now, if I use a bichromatic driving, which is a solid line, you see you get the best of both of the worlds. So you can get smaller DC sensitivity as well as AC sensitivity just by mixing effects. And we explored this further by like looking into like a weak driving regime where you can find like a sweet spot around the resonant cases. So we fixed our drive around the qubit gaps, and we find that there are like regions of like super high defacing lifetime. But we were not satisfied with that, and we were like, okay, can we optimize our drive frequency? We don't want to have one drive frequency, but like, okay, if so one thing we observed was like, if you have weak driving, then the sweet spots appeared around resonant driving. And we were like, okay, let's relax this weak driving approximation and let's go beyond weak driving approximation and try to find out some optimized frequency. And in order to do that, we needed like quasi-energy expression so that we can find the sensitivity of that quasi-energy gap. But surprisingly, it was complicated. I was thinking like, okay, you're just going from monochromatic drive to bichromatic drive. How difficult would it be to find analytic expression of the rest energy, right? But actually it is very complicated because you go from one dimension to two-dimensional problem, and it's not that simple. We ended up finding an expression that didn't work, but it gave us the right places of minima and maxima. And that's all we needed because we wanted to know where it is minimum and where it is maximum. And just using that expression, we could find like, okay, we can have a frequency with omega star, which can give us like an optimized situation. And using that, we found broad regions of like lifetime, and we also found regions where like both DC and AC sensitivity were like super small. So you see this region here and this region here, they overlap, and this is DC and this is AC. B is DC and omega is AC. And we have a very good lifetime around that region. And we picked one of the frequencies and we found like, okay, it's not just like this complicated chaotic map. You can have also like some simple maps of broad regions where you can find like these very insensitive regions. So you have like very protected qubits with respect to both DC and AC noise in that sense. Now that's good. So I discussed about monochromatic driving and bichromatic driving. I discussed about weak and intermediate strength driving. Now I would like to go further and say, okay, let's relax the two-level approximation and say, okay, I can't truncate to the two-level, but I have to take into account all the higher levels because in my superconducting qubits, I have like multiple levels. It's not just a two-level system. And if I'm driving strong enough, I saw that if you drive strong enough, if you go beyond weak driving regime, you get nice places, right? But if you do strong driving, you also excite higher levels. So you have to take those into account, right? So let's see if, that holds. So what we did was like, okay, this is our qubit Hamiltonian in the two levels of space. Now we're like, okay, let's take full fluxonium Hamiltonian and take 20 eigenstates after diagonalization. And we check like if it converges after that. So there was no change after this value. So we were like, we stick to this value. And we found that this structure still remains the same, but you see like if you go higher and higher drive strength, you see more structure appear just because you are like leaking to higher subspace. But the good news is that it doesn't spoil the qualitative picture we saw before. So you still get the continuous manifold of dynamical sweet spots. And to do this, with the help of Dominic, who has been working very hard to get this Julia library for our in-house Loci analysis. And I think just because of this Julia thing, we were able to do this thing in like in reasonable amount of time. Otherwise, it's like a very computationally heavy task. Now, in this multi-level system analysis, we're like looking into, okay, let's look into DC, AC, and as well as doubly sweet spot, like where we have like different insensitivities, right? So 1 is the DC sweet spot, 2 is the AC sweet spot, and 3 here is the doubly sweet spot, where like you have like, you see both DC and AC have like less sensitivity, but 2 you have DC is like bad, but AC is good. 1 DC is good, but AC is bad. So we were like, okay, let's try to understand what happens in this like DC, AC, and like doubly sweet spots, right? And in order to understand, I would like to go back to my previous slide and show you like these relations of like how these things behave, right? So these depend on like the drive operator and the expectation value of the drive operator, all these sensitivities. And in our case, the drive operator is the flux operator because we're driving the fluxonium through its flux degree of freedom, right? And now in order for us to understand the DC sweet spot, what we did was like, okay, let's calculate the expectation value of the drive operator, which is the flux operator, the zeroth order, because that's the DC sensitivity. And the time independent part or the time average part is like 0. So you see there's a very small sensitivity to the DC noise just because it's close to 0. Whereas the time dependent part, which gives you the AC sensitivity, shows like it spends equal amount of time in the positive and the negative region, but if you multiply that by the first harmonics, you see it's entirely below 0. So when you integrate over time, then you get a huge AC sensitivity. So in this point here, although you get a 0 DC sensitivity, since because this green curve is like mostly below 0, you get a huge AC sensitivity. So the first harmonic is like well below 0, it's always negative. And if I pick like 2, which is the AC insensitive region, then I see that the DC goes to 3 point something in some arbitrary units, and you see like it's a huge DC sensitivity, but the AC spends like some amount of time in the negative region, some amount of time in the positive region. So if you integrate over this area, you find that it is very small AC sensitivity. And in the same way, you can also like explain the W sweet spot where you have like both DC is close to 0 and AC also spends like equal amount of time in like both negative and positive region. You integrate over it, you get small value of AC sensitivity. So so far, we studied decoherence in Floquet qubits. We have studied dephasing and relaxation with Hellman, Feynman, and Fermi. And we studied both monochromatic and bichromatic driving in two-level system. We studied resonant and off-resonant cases. We studied weak and intermediate driving strength regime. We studied multi-level effects on dephasing. And we explained the emergence of DC, AC, and W sweet spot in these Floquet qubits. So I would like to give, so after this, if you have any questions, I think I would be happy to take questions because I would like to move to some other topic. Yeah.
The entire system was a linear system, right?
No, there's a Josephson junction, so I don't think it's a linear system. It's a qubit, so inherently it's nonlinear, right?
But do you have the possibility of interacting nonlinear with another one?
No, it's just a single qubit system.
Yeah.
Which has the nonlinearity is the Josephson junction.
Okay.
That's the only nonlinearity in the system. It's the Kerr nonlinearity.
Yeah.
Can you go back to that Hellman-Feynman theorem?
Yes.
So the energies are in principle complex, right? Here, or all real?
They're not. They're real energies.
Real.
Yes.
So
Quasi energies are all real. All real.
Of this is for the system. Okay.
Yes.
I see. Okay. And why is it? Then why do we have this imaginary part in the phase sensitivity? Like if it's all, why would that be complex?
The expectation value. I mean, this UST might. So yeah, the expectation value. So the energies, the quasi energies themselves are real, but the expectation value can have like both real and imaginary contributions. So SD is your drive operator, whereas this epsilon sigma prime are your quasi energies from the Floquet Hamiltonian itself.
So HT is not a Hermitian operator anymore? Why is it?
Yeah, Dominic.
So it's that state US prime. These are time dependent states. These are their periodic Floquet modes. So what that expectation value is actually, it's a time series, and what we're doing here is we're taking the Fourier transform of that time series. So that is the kth harmonic or the kth component of the Fourier transform. The Fourier transform.
Okay, good. Thank you.
Okay.
Before you go on, maybe you can say what kind of advantages you have in terms of the lifetime of these qubits when you do this doubly.
I mentioned that, right? So if you have if you have like do this bichromatic driving, you can have like this double sweet spots where you can have both DC and DC insensitivity. So you can like increase your dephasing lifetime.
By how much?
By much more. So here in this case, we're not studying like the lifetime itself. We're just looking into the insensitivity, and we find that the insensitivity goes. So basically, you can see the insensitivity like in the region where you don't have anything, you're like up to the order of 10 to the power zeros. It's like 4 order of change in your insensitivity. That
Say again,
Four order of magnitude.
4 orders of magnitude.
So that's right. So you basically, but then if you take multi-level system, you get like of course there is some degradation. You go to 3 order of magnitude, but that's not a practical situation. So even in a practical situation, you get like 3 orders of magnitude of improvement.
That's big.
Yep, that's huge. Okay, so yeah, that's the reason I think we're trying to like build this qubits, and Irfan is trying to build this qubits and trying to see if we can control these qubits and study them like in not single qubit level, also like multi-qubit level. Okay, let me go to a different system where we are studying like the Kurkat qubits, and why Kurkat qubit follows in my topic is because it is also a driven system, but it is a very special case of driven system. So now you're driving 2 times your qubit gap. It's like an off-resonant driving. I'll come back to this point later, but before that, let me show you what the Kurkat Hamiltonian looks like. It has a squeezing term and a Kerr nonlinearity. And the reason with this Hamiltonian is interesting is because the eigenstate of this Hamiltonian are the coherent states and the cat states. So the cat states become the eigenstates when like alpha is big. So you need to have like a larger, and the alpha is given by epsilon 2 by k. So you need like a larger 2-photon drive strength. But the most interesting thing is that if you look at your block sphere, you have your coherent states and the cat state as your qubit states. And you can also check this thing by looking at the recurrence relation of this Hamiltonian, and you find the recurrence relation is given by this, and you can find the recurrence relation of your coherent states is given by this. So yeah, they have the same recurrence relation, meaning the coherent states are the eigenstates of your Kurkat Hamiltonian. And why Kurkat Hamiltonian is because they have this highly protected degenerate states, and the other states are like super separated from these low-lying states, and they are super protected from bit flip. And you have a very high bit flip lifetime in this. It's proposed that they have very high bit flip lifetime, and I'll come back to this point later on. But it is one thing to say, I have this Hamiltonian, and it's other thing to like, okay, how can I get this Hamiltonian in a superconducting circuit design and or like in a lab? And the usual proposal was like, okay, we have this SNEAL with like 3 junctions and 1 junction on side. I do a charge driving. If I do a 2-photon driving, I find like the Kurkat Hamiltonian. And this is our proposal where like instead of charge driving, we're saying you can do a symmetric flux driving of the 3 squid loop, and you can realize similar Hamiltonian under suitable conditions. But before, I would still like to go with this nail design, and then I would like to point out this parameter here. So usually the Kurkat operates at a very small nonlinearity of 1.2 megahertz. And I'll come back to this point later. But the one thing is like, okay, how do you realize this Kurkat Hamiltonian, right? So I have this SNEAL, which has like this resonator or the linear term, and I have like multiple nonlinearities. Like this n is like 3, 4, 5, 6. So it goes like, it doesn't care. It's not even or odd. It's indices. So the dominant terms are like G3 and G4, and the G3 is very important in this case because that's what gives you this squeezing term. So in order to get that G3 term, you need this complicated structure here. Now, the first thing is like the SNEAL is a driven Hamiltonian, and you drive like 2-photon drive, right? And I would like to say this Hamiltonian and this Hamiltonian has the same dynamics. And in order to prove that, here I plot the quasi-energies, the Floquet quasi-energies of this Hamiltonian and the eigenvalues of this Hamiltonian. And you see the overlap. So in a stroboscopic manner, they predict the same dynamics, both the Hamiltonian.
About eigenfunctions.
Yeah, the I will show you the eigenfunctions. The eigenfunctions are the same too at the right interval. Okay, so once I have the Kurkat qubit, I can think of like what are the decoherence mechanisms of the Kurkat qubits, right? So this was based on like the experimental. So I'm not going with the history, but I'm going with like what, let's say I have all these mechanisms, and I have, let's say, single photon effects where like I can de-excite the bath and excite the qubit, or the vice versa. That's my single photon heating and cooling. I have the 2-photon effects where I can do like excite both of them through a drive and other stuff. I have dephasing, and I also can consider fluctuations in my oscillator frequency like I did before. And the reason I consider all these decoherence mechanism is because we tried to model the decoherence lifetime in this qubit. So these dots are the experimental data. So you see it goes up, goes down, goes up, goes down. And if I just use the single photon effects, then I find that it goes up and stabilizes here, flat plateau goes up. There are multiple problems. There's a sudden rise, there's a flat plateau, and it doesn't explain the experiment. So the experiment said there's an inclination, there's a slow rise. So this one was just single photon effects with no fluctuation, and the orange curve was like single photon effects plus fluctuation. So what it says me is like we need more than single photon and fluctuation in order to explain this experimental data. Next, what we did was like we included a single photon fluctuation plus 2 photon and dephasing, and if we include all of those, we find that we can explain the experiment pretty well. The reason we can't explain everything is because we take a constant temperature, and then we think that the increasing drive strength, we're like heating up the base so that the temperature changes as well. And with a different temperature, with a higher temperature, we found that it's more stable, and then you can explain better the 2 plateaus in your qubit. We did the same thing for detuned Kerr-Cat qubit. So detuned means you have also a detuning term here, A dragger A, on top of this squeezing and the Kerr nonlinear term. And in this detuned setup, you find that if you have if you have a detuning, let's say 2.1, and if you have a large 2 photon term, your Wigner function looks the same. So these two plots, they are not different, although you have different detuning. So you can still treat your coherent states as your eigenstates and cat state as your as your qubit states. And we saw that also here, like if you go to large epsilon 2 by delta, you find your states are coherent states. But although you can treat coherent states as eigenstates, we find that there are some nice features of this detuning. If you plot your eigenenergies as a function of detuning, you find that at even integer values of detuning, you have further degeneracies, like you have higher and higher degeneracies. And these degeneracies lead to further protection in lifetime, and you see spikes where the degeneracies happen. And we could predict, like using the same parameters and the same model we had for the resonant case, we could predict the lifetime also of this detuned Kerr-Cat qubit pretty nicely. And so the thing is that we operated the other qubit at like 1.4 megahertz, and we're like looking into what happens if you go like higher Kerr nonlinearity. And we see that in the Snell case, the lifetime goes down very rapidly. So we don't have that nice behavior anymore. And then theoretically, we find that the lifetime is not good if you operate these things in the high Kerr nonlinearity regime. And that was the reason we're like looking for different designs where like we can still operate the Kerr-Cat qubit, even though like you have high Kerr nonlinearity. And we use this Snell, this symmetrically threaded squid design with this Hamiltonian, and effectively this is the same as the Kerr-Cat with this extra term here, with A dragger A cube plus A dragger cube. And we found that there is a way to mitigate the effect of this extra term by including a detuning in your, so you drive not resonant, but a little bit out of resonance, and you find that you can recover the lifetime plot compared to the Snell case where it just goes down. So with this design, we are proposing that you can improve the lifetime of your Kerr-Cat qubit even at like higher Kerr nonlinearity, which was not done before. So this is still, we have Berkeley group, they're trying to do an experiment, but we don't have the experimental proof of this thing. This is just a theory proposal at this point. Okay, so we have looked into all these things like Fouquet qubits and Kerr-Cat qubits at the single qubit level. And I think we understand better now how this dynamical protection is in these qubits. Now we're trying to move on from like single qubit level to multi-qubit level. So instead of studying one qubit, we're looking into what is the effect of other qubits, the presence of other qubits in your neighborhood on the lifetime and operation of your Fouquet or Kerr-Cat qubits. And in order to do that, the Berkeley team, they're building 2 qubit setups where like you have Q1 and Q0 are 2 Snell Kerr-Cat qubits, and they're coupled through this through a resonator, common resonator, and we are trying to study this thing, but this is at the very low level stage. We are still trying to understand, trying to formulate or like establish the theory behind dephasing and decoherence in this kind of setup. So basically what we have here is like, you can have a dual rail type using 3-wave mixing. So since you have this phi cube term in your Kerr-Cat, like G3 term, which gives A plus A dragger to the power cube, which is not present in other superconducting designs, we find that you can have a fast, swapping between 0, 1 and 1, 0 qubit if you have 2 Snell coupled qubits. So we find, and you can see this thing here. So you have very fast switching on of this 0110 if you drive at the difference up to qubit gaps. But the thing is that if you have this dual rail qubit where you use 2 qubit to generate 1 qubit, you find that your Rabi oscillation, they die down at some point. And then we find that with increasing strength of your drive, you have like this dying down happens at a lower and lower rate. And that is the thing we are trying to understand why. And I think we have a good understanding of intuition behind what's happening here. And so that's the next thing we're trying to check. And with this, I would like to summarize my talk. We studied noise correlation in couple-driven superconducting QAs. Sorry, that's the outlook. And we're looking also as a Fluke qubit as a spectator for like noise. So we're like looking to, okay, so because the Fluke qubit is tunable qubit, right? So if I like change the gap of the Fluke qubit, it could detect like the presence of two-level systems and other things nearby or the imperfections. We're also looking into operation of Fluke qubits in different drive regimes. So we're trying to understand that thing better. And going forward, we'd like to move like just from single to two to like many body qubit system. And there's a rich physics there as well. Like we can study like time crystal, we can study like dissipative phase transitions and all those things. But that's in the future. So yeah, these are the references. These are all the publications we have so far in this area. So the first 3 papers are in the Fluke and the rest are in the Kurkat qubits. So if you're interested, and if you have any comments, please let me know. Thank you.
Thank you, Vivek. So we have time for questions, although we have several. Any questions? Is that my expertise? So I ask a off-topic question. So comments. Okay. Thanks, Vivek. Thank you very much. So we will start with Roman. Is Roman here? He was here. Yes.
He is now just outside.
We're just here. So
Okay.
we have 2 minutes. If you want to grab a coffee and coming back, please.
I see.
So are you from Berkeley or from Rochester?
I'm from.
Why don't we know each other?
I was from Rochester, but I moved to Chapman with Andrew.
So you were a physics student at Rochester,
I was a postdoc at Rochester.
postdoc of Andrew at Rochester.
Yes.
And now you are
Just involved.
I'm a research associate in Andrew's group
here.
here.
Okay.
So yeah, I've been with
He's
Andrew.
he's an
Before that, you were-
affiliated
Before
scientist.
that, you were at Berkeley.
No, I'm not. So the experimental works were done at Berkeley.
Okay,
So we collaborate with Berkeley all.
because I'm a student at Berkeley. I was a professor at Rochester,
Yes.
Yes.
and I don't know you. That seems very.
I was there during COVID time.
I was looking for you.
Yeah.
So you know that.
Oh, well, I
it's
mean.
visible.
I did. Yeah, thank you. One problem was the system small. So that's the two. That's the. I think there are many kinds of work. Your work. Any of the translation. You see, there's so many levels.
Leverage that.
Yeah, that's there's so many levels.
There's energy
That's
the amount of phases.
that's one. Another kind of cubes in the
Yeah.
Yeah, but they're high.
Yeah, exactly.
Yeah. So you have data. That gives all extremely.
You talked to that's like one side, the other side.
So open your Zoom.
Well, here I am.
That's
No. Open your.
The regular Zoom,
Yes.
just
Yeah.
independent
That's-
chat.
that's the 42
I
cases.
installed about
That's you, that's
like this,
Yes.
I thought
and then just type number.
So let me see. You don't have a Zoom. Zoom software. Do
because that's this is.
you have a Zoom software? You don't. If you don't, just click on it.
No, but I usually.
Just go to
no,
the-
but I
this one.
usually- But I usually go like this. There has to be here. It's, you choose here, schedule, join a meeting. like this.
Yeah,
It
you
should
can
work.
go with that one.
But
That's
I
right.
had difficulties with this. Let's say
9,
it's
6.
9 spaces, it's automatic.
No,
But it's automatic.
Yeah, 7, 3.
Seven.
Yeah, 1, 5, 8, 3.
So maybe I'll talk to you tonight.
And
Join.
join and mute myself.
Do you have a?
So this type of thing.
Join.
From Zoom. And now I'm waiting.
That's on the page.
Forget about that.
I see, I see, I see, I see.
And I think Marina is gonna, yeah, you
You-
see, this
You have
is
to write that again.
again?
Yeah.
Oh, maybe that's. So.
Have a draft.
7/15/83. And then,
Join.
do not connect to audio, that's what I
Yeah,
want.
yeah.
Turn off my video. Please join.
I'm doing fine. I'm really sorry I cannot help you
You
out.
have to wait 5 seconds. Melina will allow you now. Yeah, she did.
So we have 30 minutes plus 10, or should I just, 35 should go.
35, yes, and 5 minutes for question. I will give you a warning of 10 minutes, such way that you know the timing as well.
Okay. And then here, I
It go with
suppose
the
to,
shoulder.
but video is on fine. but-
That's okay. Let's share.
So interesting.
And we'll go with the presentation.
Why is it so?
Because you have so many speakers.
I have a, you have a copy
You're
on?
talking-
I have
It's a top video.
Thank you.
Well, or that one, who knows, but.
This is a very, very kind.
Is that one?
Yeah.
It's,
Correct, 64, okay. So it's all these numbers to it.
Oh, that's true. Okay.
Right, so.
Yeah,
All right, so
small people.
Okay, you might just
Uh-huh.
say.
Okay.
It's fine.
So we are starting.
You're not used to that, John. I'm very used to it. It's okay.
Thank you, Joe.
Yeah.
It's fine. It's fine. Really good.
Thanks for this thing. I need to do.
You have to connect it to you.
Oh, that's cool. Yeah, right.
You did it.
Gizmo? Because it doesn't click, doesn't do anything.
It's very.
Where is it? This one. The other one, I cannot find it.
It's not this.
You cannot-
Yeah, that's. Ibrahim,
Oh.
that should be fine. Yeah.
Oh, wow, I don't have, I don't have.
I do have, I do.
Oh, you have, I left the phone, I
Yes,
thought
yes.
it's gonna be just regular
This way.
UVC. Thank you.
Hey, Mark. Good to see you.
Casual today, huh?
Sorry.
On casual today?
So,
For the beach one?
I was in a white shirt and tie on Monday. Full suit. Normal clothing, and today I'm ready to go.
It's not doing anything. Why is it not changing?
Here to join us.
Some unusual things to do with my wife this afternoon. I have a brand new friend. 3 weeks ago.
Changing without changing.
3 total. I haven't.
So,
My daughter.
I know this is my time. So maybe I should stop sharing and then I can
No, that's fine.
sharing.
Just got my first.
Then let's make sure.
Share
that I-
pictures.
Yeah,
Because I want.
it is kind of.
Just have your first.
Video, so. What if I close this PDF, so close all the PDFs, I'm gonna be confused.
So we can do something else. If you click share, you can share the entire screen and it is much easier.
Oh,
No,
that-
we didn't have this
Forming
screen.
the-
Talk.
So it should be just.
Is that from the
Up names,
Yeah.
youngest or
the
middle?
oldest.
Yeah, that's the only.
Yeah.
Yeah.
But then why is it not?
Youngest is-
Just click.
Oh,
Share.
share. Why is it not moving?
He's not even thinking of getting.
Oh, really?
You see, no, my mouse is there, but why is it not moving?
Actually, because it's a different one, so because
Yeah, let's close.
20.
it's not closing, so it's a different
Right,
one.
so
So
it's
you have to-
different. Right, let me just close all of them because it's too much.
How long it is?
I just stop.
I've been married, about 30 years.
So I'm sharing and sharing. Yeah.
Incredible, that's awesome.
In a couple years will be sort
There's
of
only
like.
one thing to change, but that's the one.
That's amazing.
Maybe that'll click work. So now like. Here, this is the one, but does it move?
Yes.
Okay, does move, and
Yeah.
how about this click
Yeah,
option?
I give you.
So,
Is that one?
Oh, this one.
Let me see. The clicker does
Oh,
not
we're
work,
going
but the laser
to-
pointer is.
Going up a white paper. And. Yeah.
I can do this, so it doesn't work?
You haven't talked to our guys. It's fine, but some of this, I was telling you.
My apologies, we phoned Roman, but we have technical issues. Really? Oh, yes, it's working now,
How
maybe.
about pages?
Pages,
Don't work.
no, it doesn't work.
All right.
Let's try again, maybe.
So, John.
This is pages?
No, it does not work.
Interesting.
Right, pages don't work. But
Where is the control?
the con-
No, there's no control. You have to use the last.
Okay.
how do you switch pages?
Here.
Oh, really?
Yeah.
So I thought people were switching pages.
Yeah, but we don't have the control.
Okay, okay.
It's mostly
I
already.
can understand.
Alright.
No, it doesn't work.
Practical limitations of that. I mean, that-
This works,
Pointer works.
pointer works, but pages doesn't work.
Pages doesn't work, okay.
So I have to go by this, thank you. All right.
So,
Yeah.
After the technical challenges, we are 6 minutes behind the schedule, that's fine. And our next speaker is Roman Boni, yeah, right? Boni, yeah, from Chapman University. And Roman will talk about Mermin devices for generalized decay states.
Thank you. Thank you for inviting me to give a talk here. Sorry for the delay again. I'm gonna talk about things we've been working recently with my co-author Tom Kephart from Vanderbilt University. So there is a recent preprint on this. And the subject matter has to do with violation of Bell inequality in a sense. And related subject. And the main idea is that there are known results for violation of Bell inequalities, which is to tell you how basically quantum the state is. Sorry, there's some random pop-up here. How quantum state is. And we have exact results for many cases, in addition to what is already known in literature. And as a second part of my talk, I will talk about something called Mermin devices, which is a way to show how classical description in terms of local hidden variables clashes with quantum mechanical description, specifically in terms of so-called instructional sets. And again, we have exact results. And the interesting thing is there is something unexpected there, which we don't know the answer yet. So I will say something about most people know this stuff, so I'm gonna skip much of it. And what I would like to say is that GHZ state and generalized GHZ states, this is a known family of quantum states, are known to be maximally entangled, which we disagree with that word maximally there because we have our own take on that, but that's a separate matter. And they've been a benchmark for comparing all other quantum states to them. And the Mermin construction and so-called Bell-Mermin operators that I'm going to talk about, they are tailored towards these states. And when you look at the expectation values and the bounds of absolute values of there, the question arises is, are those operators the best possible that you can use? I'm not going to address that point. We have some conclusions to that, answer to that question. But we're going to proceed with the standard approach, except that we're going to look at the family of so-called Dickey states, which were first introduced by Dickey from Princeton, and he was looking at some astronomical applications. And the interesting thing about them is relative to the generalized GHZ states is that they are robust. For instance, when you knock couple, if you project the state on some vector in a space, you lose all of entanglement in the GHZ states, but you do not lose that in the decay states. So in a sense, they are robust, that they preserve some entanglement, not the full of it. And our goal in this research is actually one part of the research is to replicate Merman's calculations for these Bell-Merman operators for all possible states. Now, of course, this is a grand plan, but we'll show that we have actually infinite family of result within the infinite family of states. So proceeding now, before I proceed, there is one comment that if you look carefully at the Merman set of papers, and I'm not sure that many people of you are familiar with that. I know at least one person is very well familiar with that. I would assume Kai would know this by heart. That's his specialty in a sense. And when you look closer in those set of papers, what you would notice is that when you design these so-called Merman devices, you need to find the set of commuting operators for which a given state is the eigenstate. So that would be the crucial point for us to proceed. And it's not a trivial problem to find the maximum linearly independent set of these commuting operators. So I will show you the many results. And then as a second part of our goal is to, with respect to the Merman devices, we would like to know if the conclusion that he had, which is if you have so-called instructional sets, which is the information you give to a particles that they carry to the detector, and when they arrive at the detector knows what to do, blinks with a red or green. We formulate slightly differently than Merman, but it's equivalent in a sense. And these instructional sets will fail to predict the quantum outcome, which is what we usually say they are insufficient, these hidden local variables. But for the family of states that we are considering, we found there are many states for which they do work, which is strange. Maybe that's an indication that these states are closer to being classical rather than quantum. So there is a degree of quantumness, which is a separate paper that we have. So let's just proceed, and very quickly we start with just making sure that notations are all set up. So I denote E1 and E2. So here is my two states in the qubit space. So everything is in qubits. We have n of them, and I'm gonna use these notations for the basis of the n-dimensional Hilbert space. These indices run between 1 and 2. And GHZ states are these ones. So you have the tensor product of all E1s plus tensor product of E2s. Notice I'm skipping the normalization factor. It's completely irrelevant in what we are doing. Of course, states should be normalized. So here's an example. So GHZ states, when you have something like this, or if you use 0, 0, 0 plus 1, 1, 1, that's your state. I call them U sub n, and U sub 4 is a generalized GHZ for 4 qubits, so that's pretty standard, pretty simple. So the decay states, which, as I said, they came from, well, both atomic physics, actually astrophysics as well, are the following. So you have a product of E1s, you have a product mostly of E1s, let's say. You insert E2 in certain positions, like here, here, there, and you insert them in these positions, L1, L sub 1, L sub m. You sum over all of those positions, and that creates this symmetric decay states of rank m for n qubits. So they are eigenstates of simultaneously absolute value of the vector j and jz. So that's why they're useful in atomic physics. Again, this doesn't work. So example which people in quantum information space use is these are so-called W states, when it's basically Dicke states for 3 qubits. Here is this, here is that. So it's basically dual of each other. You replace ones with twos, and they're called W states, and they are equivalent in a sense by a transformational basis. And if you proceed with 4 qubits, you have 4, 1, 4, 2, 4, 3, where 4, 1 and 4, 3 are mutually dual. But the 4, 2 is separate. So we have 4 terms, we have 6 terms, and of course I have to limit to the number n something. So let's choose 3 and 4 for this talk, but we have results for general n. This is what I was mentioning about the robustness. So just to make sure that this is visible, if you take a GHZ state of 3 qubits, and let's say you project on the first space on the E1 vector, well, this is out, this remains, and that's the unentangled state. So you completely lost all the entanglement that you had, completely. And then if you do the same with a W state, and you project on the E1 on the first space, which you retain these two terms. So you still have a two-partite entanglement within the space 2 and 3. Because 1 just goes for the right, and this is 2, 1 plus 1, 2 is the same as 1, 1 plus 2, 2. So you retain some robustness, you have some robustness, and people do have a heavy use of this for measuring multipartite entanglement as well as for error correction in computer science. So what we're gonna do, we're gonna work with slightly different states, but only slightly. We call them generalized Dicke states, and they are different in one important aspect, which is if I take, so before I had, let's say, 2, 1, 1, 1, 2, 1, 1, 1, 2. Now I'm gonna add a dual to it when I flip by the symmetry every 1 bit into 2 and every 2 bit into 1. But then I can prescribe arbitrary complex coefficients to them. So it's a subtle point whether they are equivalent in sense of entanglement to the previous states. Some are not. That's a separate thing. But they're very, very similar. The reason why it's much more convenient to work with this will become clear in a moment, just generalized states. So as I was saying, we need eigenoperators. Even though this is not a conventional word, by eigenoperators, typically in mathematics meant something else. So I use this as a shorthand term. So let's say we have some eigenvalue equation. I will call my operator C, and they will depend on the vector V, which is the state, and it will act on the same vector V, create an eigenvalue and the same vector. And then I'm gonna look at the sets of these operators. The important point is that all CJs commute with each other. So in other words, if we do measurements, you can measure them simultaneously. That's the whole point. And then the point we will try to address is how to find the minimal sets of these linearly independent things. So again, I'm using also notations for the basis in terms of Pauli matrices. I'm taking tensor products and I use this like this. So what would be our approach? We start with the operators to have this form. So this is just a coordinate times the Pauli matrix, and these are complex numbers. And we're gonna include only sigma 1 and sigma 2 as a standard in this Mermin approach. So the symmetry that I mentioned for the generalized Dicke states come in the form of the following. So we need an operator that is exchange of E1 and E2, up and down spins flipping. And if you have a state which is symmetric under that, then if you take an operator A in the form of the Pauli matrices products, you use these standard rules, and you will find that every single V that has this symmetry is the eigenstate of this operator with a plus or minus sign depending on the mod 4, either mod 2 in this case, mod 2. And here n2 is the number of sigma 2s in A, because if you have I squared, that gives you -1. That's the basic reason for that. So that was the reason why we symmetrized the states from V and M to V tilde and M, but I will use also V and M non-symmetrized later on. So we proceed and we ask what are the results. So here is the list of results. The results will be written in the following form. So three rows. The first row is a list of operators. Second row, let's just ignore for now. And the third row are eigenvalues. So for the GHZ3 state, we have these three operators, which is from Merman, this is well known, and their eigenvalues are as such. Then for the W state, or for first Dickey state, you have only two operators plus linear combinations, but that doesn't count. And then you have two eigenvalues, 1 and 1. Now, you are, well, and then the same for the 4 qubits, the list becomes longer. There's the state list of operators, much shorter for V, list of operators, again, much longer for 2 and eigenvalues, etc. So then, yes, I'm sorry.
My apologies. If you go to the previous slides,
Well,
so
you see, I was about to go to the next one and didn't go, so maybe it's the same problem. Something gets stuck. Why? Okay,
yeah,
right.
So
yes.
so in the case of the GHZ state, when you have such an eigenvalues, right?
These ones,
So
yes.
yeah, if you go with the sequence of the measurement, you will get the contradictions, right?
That's the
In
basic
the case
point.
of in the other case, when you get 1-1, how do you get such a contradiction?
This one,
Yes.
I will show you. That's actually a tricky point. That's the whole point of doing that. But you are absolutely correct about this. And then notice there are some eigenvalues 0. So that would be also important. Some of them are just all positives. So it's a careful dance with all these eigenvalues you need to design. So the design of the machine, of the device, depends on these eigenvalues. It's precisely that. So what I'm gonna say is, so far, I look at list of operators and then I say, oh, now I can create any linear combination by a known theorem from linear algebra. But then the problem is that for the Dickey states, you cannot, so if I go back to the table, maybe it will become clear. So I retain my sigma 111 here. This is Dickey states, this is GZ. You retain this operator. But now instead of these three, you have just one operator. But this is not a random operator. This is actually a sum of these three operators. Turns out there is a severe restriction. And the same goes for the 4 qubits, etc. So here is those operators, sigma 3, and then the same for the sigma 4, and then there are many others. I will say something about them. There is something about that those additional operators are not factorizable, but you can look at them, let's say something like, let's say pick up this one. If you select the first position at 1, 1, 1, 1, you will have 1, 2, 2 plus 2, 1, 2 plus 2, 2, 1, which is just tau 3 acting on all remaining spaces. So there is a factorization with respect to space 1 and everything else. So there are various relations between them, but then that's the crucial point. So as I was saying, if you have a set of operators and you look at the linear combinations in order to do your measurements, fine, that's what you do. But interesting thing, and that's the key point in the Merman, besides the set of eigenoperators, is the nonlinear relations between the operators. So here's the one that Merman uses. If you take a product of these sigmas, you obtain this with a minus sign. And that's the crucial minus sign, which is everyone knows about who looked into that, which creates a contradiction. So then we ask, what are the analogs for the 4 qubits, etc.? Well, here they are, not too difficult to guess, but then there are interesting ones. This is what I call interesting. Even back in the Merman case, there is this relation, which is not a trivial statement because this is an 8x8 matrix, product of 3 sigma ones. And this is certain function f3 written like this. Who knows why? This is the function. And this is another operator, 8x8 matrix, which I showed earlier. It was a sum of 3 sigmas, sigma 1, 1, 1, 2, 2 plus permutations. And then there is something similar with f4. There are identities like this. Now, these functions are interesting in a sense that they are unique functions if you restrict them like this. If you look, so this is the plot of these functions. If you look at the integer values indicated here by dots, they take integer values. And that's exactly what you need for the measurement, because you either measure it's 1, 2, or 3, depending, because there is a sum of 3 operators. So from -3 to +3, or from -6 to +6. And here they are all this. Well, of course, this is odd function, so you have all these plus minuses dancing around. But the point is, it's only integer values. And this is not an integer value. Well, it's 1, but this is not 1. It's close, but it's not. So, and it's exactly what you need to skip every integer, every second integer, and so on. So these functions play the role. I will show how. So then measurement devices. Very quickly, as I said, you need, so the device consists basically, you have n particles, well, in this case, 3 or 4, they emitted from the source, and they carry with them some information, classical information, which will be called instructional sets, and then you're trying to predict the outcome of the quantum result with quantum measurement with those values. So those instructional sets, I call them psi and eta here, they would be just numbers -1 and +1, or in the terms of Mermin, that would be red and green lights. So that's that. And those second line in the tables that I mentioned, they were these instructional sets. So for instance, let's say here for the Mermin, all you do, you replace sigma 1 with psi 1s, here it is. You replace sigma 2 with eta 2, and here they are. So that's all there is to it. So now, following Mermin, what you do, you say you would like to see whether there is a contradiction. So, for instance, specifically for GHZ, this is, of course, what Mermin did, you have these 4 equations, famous 4 equations, and then you say, well, can you solve them simultaneously when psi and etas are -1 and +1, nothing else? No, you cannot, because there are only 8 solutions. Well, there are 64 possibilities, 2 to the 6, because you have 6 variables, and there are only 8 possibilities that solve 3 last equations. But if you look at all of them, the first 3 columns, you have an odd number of -1s, so their product is -1, but unfortunately you need a +1. So no solution possible. And that's comes from this minus sign over here in the identity. Okay, so in other words, we say that it's impossible for those 4 experiments with those 4 operators to have instructional sets to predict what would be the outcome of the quantum measurement. With 3 experiments, you can. The 4th one is a deal breaker. So then we say, well, can we repeat the same with the 4 qubits for GHZ? Yes, you have a system of equations and you proceed. And I don't have solutions here because there are partial solutions because there are too many. But basically, you have to solve these equations. And actually only one line in a row. But what you do, if you multiply the equations in each row, so you're going to get 8 equations, and here they are, and they're all contradictory because you have a plus or minus 1s to certain powers, including 0, squared equal -1 across the board. So it's, again, impossible, but this is known, even though slightly different form, but it's known. There is nothing there new. So now, the new stuff. What Ibrahim asked is how we gonna do this with this eigenvalues 1 and 1. Well, because it's an eigenvalue 1 for the operator tau 3 written here, not for these individual ones that we had before. We had 4 because there was this operator, there was this well, here we are. There was this operator and 3 others, but now we pack these 3 operators into 1, tau 3, and the sum should give eigenvalue 1. Okay, well, here are the Mermin instructional things. So now you have to solve only 2 equations. You think, how difficult could it be? You just have to solve this and mu3 equal 1, which is this number. Again, you are solving on a space of minus and plus, minus and plus 1s only. So 24 solutions. Unfortunately, all of them are wrong, because none of them will give you a positive product in the first 3 columns. So it's, again, impossible, but the design of the device is, so that's a distinction, if it was not clear. You design a device that measures this. not individually separately, each of these operators, but this sum, because this sum is the eigenoperator. Now, how you do it engineering-wise, don't ask me, okay? Sorry, I have no clue.
Because it's some sort of non-local measurements that you have to perform.
But if you do that, that would be precisely the good thing. So then, of course, so that's again. And then the way to look through the functions F3 was again to use this integer properties of these functions, and to see, well, you need to solve this. So mu3, so function F3, this must be 1 for the eigenvalue, and you go through all possible solutions on those graphs that I showed, and you again rule out. So that doesn't work. All right. So then we proceed with the 4 qubits. I'm gonna speed up because I'm sure I'm out of time soon. We proceed now with the first decay states, which you have 4 qubits and 1 E2 among. So 1 E2 and 3 E1s. That's what 4-1 is. So you have these 5 operators, and here are their eigenvalues and their instructional sets. So then there are various things here, and this is the equations you need to solve. There is some choice that I'm gonna ignore for now. And the strange thing is, you can solve these equations. That's what I don't understand. You can solve these equations in terms of Mermin for all of these operators. So how many? 5 operators, as I said. You can solve, so there's no contradiction here. And that's not the only case that there are no contradictions. So in other words, the design of the Mermin device in exactly what he did does not rule out that thing. Well, we know it should, but something else is needed. I don't know what. I mean, what modification to the device needs to be done in order to rule this out. Now you may think, oh, well, that's maybe a pattern for all other states. Maybe GHZ just lucky, and then maybe that's why he did that. Well, no, because if you proceed now to the next decay state, which is has a bigger list of these operators, and then now all positive eigenvalues. In fact, you can solve all these equations, and you will show that there are solutions. There are many solutions, and sorry, there are non-solutions. Before we had solutions, now there are non-solutions, and you cannot operate this device predicting the quantum outcomes. So we have similar patterns for higher order decay states, but I'm gonna switch now to something completely different in the remaining, I don't know, minus 5 minutes or something, whatever the time is. This Mermin approach was kind of tied up with Mermin operators, or Bell Mermin operators, and they, for the sake of time, I'm gonna look at those operators here. So let's say M3, that's the third Mermin operator. You have 3 operators. These are simultaneously Hermitian and unitary operators, so they square to identity. And they act on the space indicated by the label. So there are 2 of them. Well, there are 6, XA and YA. This specific combination is famous, and it's not a typo. It's a 1 plus and 3 minuses, or could be vice versa, 3 minuses and 1 plus. And it's a very delicate machine. If you just flip one of these signs, everything just collapses. So, and then the generalization for the M4 is something like this, which is actually different from what Mermin uses. He uses half of it. Basically, he has 4 terms, but we have 8. And an important point is, if you look at the operator norm for these operators, they never exceed certain number. Well, they're bound because of this, and then you find that for the Mermin operator 3, you obtain bound 4 because number of terms, basically. Each term can contribute at most 1. And you have 4 terms, you have 8 terms, and you get 4 and 8. So now the point is, how close can you get to that bound? In other words, how quantum your state is. The bigger the number, the more quantum the state is, in some sense. Well, GHZ states actually saturate those bounds because they are eigenstates of these operators. turns out they're exactly eigenstates, so that the expectation value would be precisely, I call the expectation values mu3, would be exactly 4 and 8. So they are maximal in this sense. They saturate. And this is true for mu sub n and u sub n for arbitrary order of those. All right, interesting point, and that's important point, is that actually these generalized Dickey states, they are zero modes. Because when you look at the operator M3, shown before, acting on those tilted symmetrized Dickey states, you obtain exactly zero. So it's almost the worst possible outcome that you can get out of that. Okay, but that doesn't mean that when you are allowed to wiggle these states within a class of the same states, you will not get anything different from zero. You will get, this is just for this one eigenstate. All right, so then what I'm going to show is this result. So what is listed here is these bounds for the absolute values of the GHZ state, which is U3 is a 4, as I said. For U4 is 8, this is known result. Then everything else is new. And what is written in black color is the theoretical, as an analytical calculation. What is in blue, well, it's also analytical, but this is numerical. Now, what is peculiar, there was some obscure paper back years back, when they had this actually slightly wrong. They had 3055 number, but they never had these squares of 41, etc. So it's kind of interesting how these exact values emerge from solving some high polynomial equations. In this case, I think it's a quartic equation that you need to solve. But these ones are exact. And I'll just show you basically. Oh, and then there are others. We have other results of the same kind. And here is a peculiar. Maybe I should show the picture, the table first. So in a table, ignore this column and this column. This is the n, and this is m for the generalized Dickey states. And what I just showed was that we have 4.5, that was 9/2, and 6 for the Dickey states. This is the maximum you can achieve. This is analytic calculation, and this is approximation to the analytic calculation, which is peculiar that every second row, meaning skipping mod n and mod 2 in n, you obtain the exact perfect match between analytics and numerics. We do not have explanation of that, and they are not just integers, half integers. There are things like this where that's exactly right, and I will show you what the approximate solution is, approximate bound is. But every odd ones are not. But approximation is still good. So, for instance, here it's relatively good. Here it's not. Well, this is perfect almost. This is much worse. And we have a table that extends to much, much higher. These other columns that I mentioned here, they have something to do with the degree of entanglement of states. So the example of that solution is, it's as bizarre as it may look. The solution is this. This is the bound on the expectation value of the Merman operator. Here is this, well, something. And then Cm is the finite sum with the exponent where, of all things, Am is a 4/3, and then there is this bizarre finite sum again. So why? Well, I don't know. But how you prove this, I'm just going to sketch in a minute or something, how you sketch this. In fact, you first simplify your problem as much as you can. Remember, we had 6 operators, x1, x2, x3, and the same for y's. It turns out to have a maximal bound, it's enough to choose all of them equal for the Dickey states and for GHZ states. So you just choose, so you basically have 2 simultaneously Hermitian and unitary operators, x squared equal y squared equal identity, thank you. And you expand them in Pauli matrices, these are real numbers, so they live on a unit sphere, these 2 vectors, and then you just plug in and calculate, and what you obtain is you obtain these polynomials. Polynomials in x3, which is the component of the sigma 3 matrix, x3, y3, but there's also x1, y1, x2, y2, but they always come in this form, here, 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 and there, sometimes linearly, sometimes quadratically. And then if you carefully look at that, you will see that the maximum always occur, maximum minimum, because it's sign reversible, you always obtain when it takes its largest value. But the largest value of this is something like this because vectors x are in unit sphere. So you need to look at the sphere, project on the equatorial plane, and do stuff like that. And you will find that, so there's something saying projections of x and y in one collinear. And you will find, so now you substitute this back here and you obtain new polynomials in just two variables. Now, I can do polynomials in two variables. I know something about that. It's harder than one, but it's not that bad. And what you need then to maximize a function of two variables, again, analytically. And then when you do, you obtain something like this. So what I have here is x3, and this is the y3. So they're always between -1 and 1 because it's a unit vector. And this is for the Dickey state v31, this is for v41, and this is v42 that I was mentioning. And the peculiar feature is this 3 of 5 is right here. That's the maximum. The contour is 3. So if you look carefully, if you look this figure, well, this is a two-dimensional projection, of course, but if you look at three-dimensional, it's quite wild, going like waves if you look sideways. And there are these patterns, and there's some rotations, some interesting patterns here. But the maximum occurs here, and I forgot exactly. I think it's here, the minimum here, at this point, and then again, this point. And you have those exactly, again, square roots of 41 galore, if you wish. And you have, yeah, that's, thank you. And that's my 35 minutes. So this is the exact solutions and right on time conclusions. So what do we have? We showed, first of all, although I skipped a lot of this, how the design of the Mermin operators depends on the choice of these, that you need a choice of a commuting set of eigenoperators. And then we confirm some old results, of course, and then we have new results for infinite family of Dickey states. But the interesting questions are that some of those Mermin devices fail to fail. So they work unintendedly. They work. Mermin wanted them not to work, well, which he had for GHZ, but they do work for some of the Dickey states. We do not see the general pattern, which ones are the bad ones or the good ones from the independent point of view. But again, maybe there is some sense in which those states are less quantum than the GHZ or the rest of the Dickey family. But what we notice is, and that's our conjecture, that the smaller the commuting set is, the more likelihood is that the Mermin inconsistency will be present. So, but it's not this is only work in progress. This is very, very rough patch. And we do not have any general results how to find the size of the commuting set. How does it depend on the state? So that's that. And then last slide, we, of course, did this, which we just had, the bounds for the Bell Mermin operators for Dickey states. But there is this interesting periodicity on mod 2 that I explained that exact results match perfectly with very rough approximation in a sense. There's a lot of serious and differential equations hidden here from your view how we arrived at that calculation, but that's a separate story. So we don't have the explanation why there's this periodicity. It reminds us a little bit how there is a strange periodicity, so-called Bott periodicity in topology, but it's probably not of the same kind by a mile. So thank you for listening.
Thank you very much, Roman. So we have time for a couple of questions. Is any? I already asked my questions.
I can ask more.
Oh, okay, nice. Yeah, of course. I was thinking about how to perform the measurement actually. And
You would be the man.
that requires non-local measurements doing some sort of entanglement creations. Either you have to do it non-linearly or you have to do it in linear optics and probabilistic way. So we definitely, I will approach you and maybe.
Okay, probabilistically, you say.
Yeah.
Yeah, that's a possibility.
Yeah. But can you remind me of what Of course, the GHZ, I recall well, what sense of quantum mechanics is approaching and targeting. What about the generalized form of these? Are you?
Of GHZ, you say?
Yes, I recall the GHZ that is.
This is for 3 qubits, GHZ
Yeah,
standard.
absolutely. And for these generalized situations of the memory that you had, each memory devices. So are you challenging, for example, the contextuality of quantum mechanics? Are you putting a higher bounds?
I'm not
What-
challenging anything, let's
Yeah.
put that way first, but the motivation for the paper was basically to try to see if we can go further
Okay,
by specifically in calculations. Now, we didn't know that there's gonna be some headaches, like something works, something doesn't work, as I mentioned, some of the things you cannot do it. I'm not saying that we had, a vision that some states will fail and therefore maybe there is some loophole somewhere in logic of, the stuff that you mentioned. No, we just straightforward calculation and presenting the results without any hidden agenda. So
I'm looking for Kai, but maybe
He
the
just
three of
walked
us,
out.
we should
He just
discuss.
walked out.
Okay,
yes,
so let's go with Marco and then Dennis.
Are those all the cases when you
are
have
those all the cases you said?
only
Oh.
cases when you can find that you can solve those equations? Would you expect that
About
solution become
bounds.
more frequent? Yes. More frequent when you go to the higher dimensions, more multi-particle states?
So my gut feeling is this is pretty much it. It's hard to get more solutions out of it. We tried, what of course doesn't mean anything. The reason is that when you look at the Merman operator, it has many terms. So when you look at the polynomial degree, it becomes larger and larger. And we were just lucky that this was a first order polynomial and we could solve it even though it was horribly bad. Mathematica didn't want to do it. You had to do it in some substitutions. But my prediction is if you go higher, you won't get those exact results. But the approximate results are exactly right for the even ones when we confirm them numerically. So we did the numerical calculation up to n equal 10 or 20, I forgot, maybe 20, something like this. It's not too hard to do 20 qubits.
On the paper.
Is what?
On the paper.
Of course, okay, of course, right. So we do have that pattern that I mentioned, it appears. I don't think we can do analytically. If anyone can, well, welcome to. I do not have any deep insight why would that be the case besides the counting the degree of polynomial. But
Dennis, let's go with Dennis and after that.
I have a
will be
question
last
to make sure that I understood this eigen operator. So it's like given a vector, you would like to find the
right, so
largest linearly independent set of commuting operators, right? Am I correct?
choose a vector v. Say among all operators acting on the right size and right properties, what are the operators for which this v is eigenstate? Well, there are many of them. Okay, so you have to find a basis of those operators. It's infinite set actually.
Yeah, of course.
Okay, now among that set, you choose the subset of mutually commuting operators between them. And that's the finite set if you remove the linear combinations. That's how you get down to a finite set. So let's say for GHZ, you get 4 operators. Well, it's actually 4 or other choices for dual. You flip 1 and 2. So there are 4 operators that are in the commuting set. Every operator commutes with everyone. And they all have common eigenvector, which means we can measure them simultaneously. Now they have a different eigenvalues, plus or minus 1. So that's the pattern. I know I went too fast through that part. So the commuting set of eigenoperators is the set of operators for which this vector is eigenvector, and they all commuting with each other, which is not a standard definition of eigenoperator. Eigenoperator is something higher order definition in math. I'm abusing the
That's a
terminology.
non-linear eigenproblem, right?
Right.
Oh.
I'm abusing the terminology. Yes. It was just easier to say it's easier to say eigenoperator instead of saying this is the operator for which given vector is an eigenstate. So it has nothing to do with nonlinear.
So we are running out of the time. I'm
Sorry.
playing in the coffee break if you can ask the question. I'm so sorry for that. So let's thanks Roman. Thank you very much. And we'll have the coffee break. Let's be back by 10:45. 15 minutes.
Who this I should return?
Is good. Thank you. Thank you.
But I came unprepared. I do have a. I didn't
No
realize it.
worries. It's me.
Sorry for that.
Yes, please, sure.
Ah,
By the way, it looks like the answer to the universe is not 40, we know 41. That way takes away from this,
I didn't think of that, but thank you. That idea.
not supposed to be.
Yeah, what do you want?
Is it?
You need that or?
It's,
So, sure.
this is like a flame.
Vincenzo is
This
one
is
guy
right.
who wants to,
That's it.
start.
What? You're gonna.
Yeah.
I was thinking.
I know people that those live, but, it sounds like some people. will go around too.
I need to go to the beach with Bob and Adi because they need
Barely,
to.
yeah.
But
But
I was thinking about
But if you know.
even a crazy idea.
Yeah.
We can just have a talk about. Stops.
Mhm.
There's all that in, I mean, no one played that in the special emotion.
Yeah, yeah.
Yeah, you can just try to do that, like Humphrey Brown Street, but just do it. Real situation, it's not difficult.
The thing I've been wondering is there's. For the photon. What really problems of the photon we
The hip joint?
to get this to work? Because I would assume that it comes out.
Yeah, and then
Same
this
spectrum.
You can use it like 50.
Or I could,
You mean like take the star, filter it, filter
Exactly.
everything?
Because we with the Hungu mandal is that you can do the post selection identically. Because if you just propagate exactly, it's the situation will be the one that you do the post selection.
Hey, Mark.
Yeah, the thing that was interesting about what he was talking about yesterday was that
Say again?
he wasn't doing any filtering.
Oh,
Yeah, the
congratulations.
second scenario.
Yeah,
And the first scenario.
Oh, wow. Okay,
Yeah.
very nice.
But in this part.
You must be very proud.
They
Yeah.
agree that, that's how we do standards. Get everything to match up. You
Oh,
put a
wow, sweet. Very nice.
10 nanometer
Congratulations.
spectral filter, you get it.
Lovely.
Yeah, I mean, that all sounds very reasonable and quite interesting.
is it just this one?
You need an array, which I think what you have.
Yeah.
Done is.
physics quite open from the other day.
Something like.
Yes.
Sensing.
Sorry?
Oh, okay.
It's gonna
With
load.
your new
Squeezing never goes away.
camera.
And then when you wanna just go
Yeah.
forward, you can just.
So there is, doing it, I agree. I mean, putting it,
Okay.
stars is awesome. It would be a little easier to start off with maybe, two incoherent sources.
No, no, of course, I mean, this was ultimate thinking, and
Yeah.
absolutely, I mean, you're right.
Yeah,
We
to
can
violate
apply
Bill.
it within the laboratory, and maybe the proposal will be even broader, and we can, that will be the first step, and then will be really implemented on resolving an object.
Yeah. And I mean, you could imagine.
That's very interesting.
You have a beam splitter, and then you align two LEDs.
Yep.
Behind the beam splitter, and you essentially are able to translate one LED. To get closer and closer in terms of what's being coming out the other side. And just showing that you introduce this additional photon, you still resolve.
One thing that I'm still.
Gradually fade away.
That's the question.
Right, so there are certain things with thresholds, like you mentioned the Bell one. Also, like concurrence has a
If you don't
threshold
notice
as well,
them,
like there is positive or
Yeah, what I
zero.
mean.
Yeah,
There's
yeah.
a whole class of states.
It is something that we should
So
ask him.
I imagine that's easy to calculate though, because you know the central.
Like, basically, if you have like a yes,
We
no.
always
question,
have done the feature information, always.
but those are all sort of.
And then I did the Taylor expansions, and then calculated the
Yeah,
feature
there we
information. And we was based on
Yeah.
information that one is a psi plus, the other one is a psi minus.
Yeah.
encoding.
Yeah, there are certain things, like if you have like a.
Come up with the white paper.
You lose one
Yeah,
photon.
The other thing I was thinking about is I want to redo the white paper I sent you because I did it too narrowly. I just basically talked about gyroscopes, but basically, what could you do with an ultra precise frequency measurement?
Yeah.
Like what Adi was talking about, where, and what we talked about earlier, right?
Yes, yeah.
The Berry frequency, right? Yeah. And I don't think anyone's actually done the Berry frequency, so we've seen rotating wavelengths, but that's not really a Berry phase, so you can imagine interferometric that you're actually just changing.
You're called.
There you go.
This is that
Yeah,
discussion.
this discussion like 6
Years
months ago,
ago.
a year ago.
Yeah, I get a
And so
copy.
we have Berry frequency, we can imagine doing with these rotating OAMs, we have the gyroscope, we have something I was talking about with Dennis last night, because he's like, well, didn't you make your own? Just put a massive object by your interferometer
Yeah,
and move, and then I was like, well.
and then see the effect of.
Yeah, so you could actually see the redshift of the oscillating. You should see a redshift change. I mean, that's cool in and of itself,
Absolutely,
right?
yeah. So why not? I mean, let's do that. Let's
Yeah.
expand it.
So I expand that as then what you were talking, the GSO thing. And so anyway, I think if we had 3 or 4 of those.
Yeah, I think it will be 90% forward.
Yeah.
They can have slack forward.
Yeah.
You know,
Yeah,
I think they will find.
yeah, and they may say, we like these two, make it into one. right?
Exactly. Or, yeah. Or maybe we lost all 4.
Yeah.
Yeah.
Right.
It's, yeah, that's what we.
Yeah.
I will see you.
Okay.
You can have permission if you open your,
Do it right now.
if you go to your,
So, what time are you going to?
using the address that
2:30.
2:30. Oh, okay, yeah.
I sent
So,
to you,
we
right?
just-
Let's try.
How we work.
Okay, this sounds perfect. So, okay.
I don't know why these things never work for me.
I will give them right at 2:30,
Okay.
so we can work on.
Or I can turn it around the other way. Considering that these things never work, I don't know why people keep using these. Not the one for me that they do.
okay, so now you're gonna switch your Google Drive to your, you have a Rochester, you have like a Rochester address
Sure.
in your Google Drive?
I don't even know how to do it. Oh, I don't use Google Drive. Or at least I don't know. I gotta learn them all.
Let's just request access.
Is it that already? Get an email letting you know.
All right, let me try that.
So. Okay, I can take you there. But I'm probably gonna leave you San Jose too. Okay. 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 Yeah, and so. Yeah, just meet here too. They're good? Yeah.
I really will just.
Perfect. Yeah, so then, I guess what we would need though is, because I live in Carlsbad. We need a way to get you back.
Yeah, we can do.
Probably coming late, so I have it's an open house with Daisy for the school, which is.
What time are you coming back from Angel's place?
I'm not going there until probably 6 o'clock, so I don't know. I'm not 100% sure if I can make it. I'm gonna try to make it for the dinner. If I am there, I can certainly bring people.
Okay, because I can take some people, it's just that, you know, we live in Carlsbad.
No, that's no.
It would be like.
If I'm there, it's like.
Okay.
Yeah, I'm gonna pull everybody attention and try to make sure we can pair up with drivers, everybody gets a ride. Or we can also do Ubers if there's a problem.
Because I can get, I thought. Just getting back.
Ubers on the way back, if it's fine. We don't have enough carpoolers.
Okay.
But yeah, I can take people as well. Car. Do you have a car, Matt, or?
Yeah, but I like to say, they're don't have fulfilled my, it just like else. There's still six, so we could try to see if I can come up with that, but I think it's too late.
It's fine.
Yeah, so I'll probably be there, but.
Whatever
not
works.
till later.
Okay, great.
Okay.
2 o'clock.
Thank you.
Okay.
See you at the pool.
I'm not after that.
Are you gonna give a ride to some?
I reacted appropriate.
Okay.
No, I reacted in the same spirit in which you reacted. Okay, so.
Good.
You're good.
Okay.
So that was good. Okay, that's good.
We have a phone number. So I'll give you a little presentation, show you the variant.
On to a channel.
I Your Mac account and your Gmail account. So you just go to your Gmail account, Bob, and then. Okay, you should be able to open.
But I don't know what we mean by a Gmail account.
You have a Gmail account.
Oh, yeah.
One of the most
Beautiful
papers now.
You want them?
Beautiful,
Right.
Maybe that was has.
Download it anyway. There's no viruses. Cause it's too big, cause it's a whole book.
Yeah, thank you.
Enough space.
Yeah.
So, so we're talking about, for example, this is the Y. Y.
So let's make sure it's here.
Yeah.
Past. This way has a kid state. Like traditional kids. And so it would have like a cancer.
There it is.
There it is. So.
It's entirely downloaded. Thank you.
Perfect. You're very welcome.
Oh, now I have to read it.
That's right.
Yeah.
But hopefully you'll enjoy
That's
it.
right, that was the hard book, and you have to carry it with you.
That's true.
This I have not. You took the.
Yeah.
Like,
But the hard book is nice for like your airplane. You know, like look at that on your airplane.
Right.
Like she's
Better than.
That was my thought when I bought.
Still
There you go.
Okay, is it, do they, just not all the degrees of freedom they can hear, is that why?
So, and also the client, so yeah, just use the way, but again, this is important, and it's not a, and this paper. I think.
Interesting, because obviously no one can do the Windows print experiment, so if there's something more
This-
practically
this is
doable.
much more
doable,
practical
it would
things,
be-
like,
it's very interesting
I
to
told you,
see.
brainstorm.
Yeah.
We just with this paper. So this is the first time it's actually. Unfortunately, this is only in Russian, there's not. So this is like. It's, you know, this is like the first time I've people try to do like. And it's the master equation approach, like in the entire.
Right, yeah.
Like, so yes. And then maybe this is something, but I think the point is not to, I think that this whole premise should not to lose the master's equations. Basically, we should just do like an ensemble.
Okay, let's do it.
Yeah, so, and because why I'm thinking this way, because we have a more recent work some sample identification. Instead of solving master equation, sort of wolf brief. You never actually work with leaf. So opposite. You never practice a question and would.
With it is bigger,
So you could
just have it rounding bigger.
Ensemble of wave basically what's so good. She's the also you need some good luck because
Okay, good.
for anything's
Yeah, it seems really be very relevant to the. I'd like to see more.
I get my thoughts together.
Yeah.
Just my thoughts together to what I wrote. Right.
Yeah, that's why this is not adiabatic.
Call them in?
It's not a fast.
We'll call them again.
Oh, yeah, Andrew, that's okay, good. Back. What's that? You're back to the. Yeah, no, that's the, yeah. Ibrahim said that's the slowly back, or just adiabatically back.
Bob and I, we have a paper in Nature Physics together on that, surely, slowly but surely.
That's true.
Your arm, not
Yeah.
yeah.
Trying to get people in.
Yeah.
Are you doing it for you?
No, I.
Andrew wants you inside.
Third session. Cases on single limits. So. Right basis, it's parts.
Okay, I'll bring the session back to order. That includes you rowdy people in the back. We're happy to have the last session of our conference, and then after Armin's talk and Marco's talk, I'll give a few remarks about our outing, just tweaking the plans a little bit, so don't run away. So we're happy to have Armin Gulian here at Chapman University tell us about Arnulf Bohm detection. So Armin, turn the time to you.
Thank you. So for introduction, I actually am with Chapman University about 17 years as of today. And we were located in Maryland, and only about a year ago, after these buildings were reconstructed and constructed, we moved from Maryland to here. So, and our laboratory as follows from its name. It is advanced quantum materials, mainly superconductors and devices, also superconducting based devices. So, and the audience here is mainly optical, and I was amazed how in this small room, small number of people, how high was the level of professionalism. So it was really, for me, it was rather hard to understand 50% of what was discussed here. But, and that's why I'm a little bit hesitant, because what I'll be talking here is a basic physics, rather simple, but nevertheless, it touches the basics of quantum physics. And that's why probably, and that was the reason I decided to talk about this topic today. So we have three of us as authors of this report, and Will Benston is MPP student, my only student whom I'm lecturing this semester, and because it is philosophy related a bit, and he was rather bright, I decided to do this final part of research with him. And Vahan Nikogosyan is one of my old friends from Armenia. He visited us recently for a couple of months. He was here. So we did major understanding of, I will tell you about next. So let's start with Aronoff-Bohm effect, and which is probably very well known. Nevertheless, I will repeat for consistency. So we have solenoid, which is really nice picture, and in many covers of I found it at the cover of Physics Today at one point. And here is a magnetic flux inside, and it is not very good from physical point of view because the windings should be close to each other, otherwise the flux will come out. It shouldn't be coming out. It should be completely imprisoned inside of it. But in which case we will have no magnetic field or no electric field outside, but we still will have a vector potential which is encircling the solenoid, and its intensity goes as 1 over r, where r is the distance from the solenoid axis. So, and this field is carless. So if you will compute the curl of it, it is 0. So, and it is interesting that Aronov and Bohm, they discovered this effect quite independently of the first group which reported about this opportunity 10 years before them, but they didn't know about this. Later, when this effect became very famous, other people pointed out that, 10 years ago, and the guys who first pointed out on this, they were developing electron microscopes, and they were computing how the lenses of electron microscope are deflecting electron beams, and they said, oh God, here is H is 0, but nevertheless trajectory should change of electron beams. So any case, Aronov and Bohm were people who brought this, connected this very closely with quantum physics. And what we have here is just a source of electrons. We can consider them as waves, electronic waves. So when they go through two slits, and we are getting them directed so that they can interfere, the interference pattern depends on what is the flux here. If flux is 0, then we have maximum somewhere here. When flux is non-zero, then it is shifting, the picture is shifted. So this was very well documented by many experimental groups, and we learn a lot about this, and that is related with the fact that electronic wave function has a phase, and phase is getting addition because curvilinear integral of ADL will add on this side and will subtract on this side. So on this side of the coil. So that's why interference pattern maximum will shift. This is about electrons, but it was interesting to see what will happen with superconductors, because superconductors are a quantum substance, and Cooper pairs constitute Bose condensate in the momentum space in superconductors with all the features of real Bose fields, and they can be described by the wave function. And the wave function has its own phase, and that's why one can expect that superconductors also should react on the presence of Carless field, which actually was also demonstrated. But the interesting question which we started to discuss with Yakir is whether or not it will be possible to detect influence of Carless vector potential on quasi one-dimensional superconductor, which is a very interesting topic, because the experiments were showing that this is if superconductor is a wire closed loop around the solenoid, then you can excite current in it when the system goes below transition temperature down, when you are cooling the system. And unless you have integer number of flux quanta here, if you have, in general case, you will have current here. And that is again because of the same reason we saw in the electronic coronal bomb effect. But it is correct to say that a local influence of vector potential at a point, you are not able to register it in any case because that is not local interaction. However, what about quasi-local? Because in this case, we have some distance and it is non-local object. The only thing is that topologically, it is singly connected and the loop is doubly connected topological structure. So the question is that possible or not? So, well, because physics is experimental science, we decided to try to run experiments, but before running experiments, we need to understand situation in general. So, to understand situation in general, we need to first discuss broken symmetry, U1 symmetry in superconductors, which I showed here as a free energy behavior when you go from normal metal state to superconducting state. So by cooling down, your free energy goes down. However, now symmetry changes, and if here in normal state, the phase of wave function of unpaired electron was able to have arbitrary values, and these values of the phase, when you have in metal collisions of electrons with each other and with the lattice, the phase is changing its value at collisions because collisions are dephasing it. However, when we have superconducting state, situation changes. Spontaneously, it can fall here, but it can fall also here or somewhere else. And when it is doing that, it stays there. And what means it? The condensate wave function or the condensate state is choosing one value of the phase. And when that value of the phase is chosen, collisions now with lattice and with each other, they will not be able to shift it from here. So this is phase angle, I plotted here. So because Bose condensate has a property of self-restoring, other constituents of the condensate are not letting this phase to change its position. So this is actually for optical community, it will be probably interesting to compare this with laser beams. In laser beams, you have coherence, but you don't have Bose condensate in vacuum because photons, as soon as they have been emitted, they are not interacting with each other. So you don't have Bose condensate. In some material, in nonlinear material, it can become Bose condensate, I mean laser beam, because then photons are starting to interact nonlinearly with each other. But the main difference between superconducting electrons and photons in laser beam, as I said, is absence of Bose condensate there and presence here. So, however, in the case when we have no magnetic field, but we have vector potential, in principle, it is possible that vector potential can affect on all the electrons in the Bose condensate. And when it is doing the same kind of effect or influence on all of them, they are not, they can change their total phase. So in principle, Carley's vector potential, because it is acting on all of them together, it can affect, and that is what happens in the in the experiments of Aronoff bomb type with superconductors. Now, yeah. So suppose that we put here a superconducting filament and would like to see what will happen with it. Then current, which I wrote this in so-called London approximation because the modulus of wave function is dropped, and I'm using here theoretical units, two times E, where E is the electron charge is taken equal to 1, and H bar is also 1, C is 1, everything is 1. So only acting functions are plotted here. So in that case, this is the expression for current density in superconductors. So we have vector potential and gradient of phase. By the way, by itself, it is very deep, again, question here, which is sort of philosophical. That's why I don't want to dwell too much on it. But you have vector potential, which is a property of external field. It is created by the current which is moving in the solenoid. But to that, you are adding a gradient, which is a property of the matter. And you are adding something which is coming not from the matter to something which is generated inside of the matter. So this is sort of the answer to it is that in top level physics, both fields and particles are the parts of some constituent about which we don't know yet enough to talk about it. However, that is a matter of fact. So let's move forward, taking this as given, because this is in physics more than half century. So if here we will have a singly connected filament, then the current is zero. Obviously, there is no way for current to flow. And that's why we need to say from this that phase is adjusting itself because A is given by current, so A cannot adjust itself, but phase is adjusting itself. So in such a manner that current should be zero. So now we can consider this with a case when we have a closed loop. Again, phase of the psi function. And in this case, in principle, current can flow because if we will integrate current over this loop, so very simple transitions from here. And gradient will give us the number of windings, full rotations. And if the 2 pi in these units corresponds to phi naught. So and curl away by Stokes' theorem will be HDS, which is a flux. So we have here flux modulus 2 pi, and if it is not zero, then current is non-zero. So it's very simple mathematics which describes moving of Aronoff bomb effect in superconducting loop here. So, and if we will compare with the previous case, we can say that topology is what differs that case from this case. So we then should say that it is topological effect. It is well known, that is very well known formulation to tell that Aronoff bomb effect is topological effect. It has analogs in many other areas, including optics. But does that mean that the game is over? Because we just need to say that topology and that's it and nothing else. So we came to the conclusion after many years of thinking that no, the game is by no means over, and topology can predict the occurrence of effects, but it will never describe the whole physical mechanism. So physical mechanism should be elucidated. And as soon as we will do that, maybe we will be able to find answers. How should we run our experiments? At this point, we need to come back to these two cases and ask question: what is primordial here? Phase is adjusting itself because current is zero, or current is zero because phase is adjusting itself. So what is the cause? And our finding, very recent finding, was that we should not consider things in three-dimensional space. We need, because in the previous slide, when I said what is driving, what is primordial, we need to consider time variable. If we need to go to quantum field theory, and there is a work by Wilson. That is Ken Wilson, who got Nobel Prize for Renorm group. So he came to the conclusion that observability depends on non-zero value of this integral. The most interesting thing in this integral, if we will go into details, is this contour. So contour is not three-dimensional, but it is four-dimensional, in which case situation becomes very complex. And we will see now a couple of simple examples. So let's do that and adopt Wilson's platform. And let's consider a couple of Gedanken experiments. So first Gedanken experiment, we have our, we have a solenoid. And we have superconducting film here, which is on red colored. So if we have here flux, then these guys will be like, what will happen? No current, of course, in statics. We are considering static case first. So we placed two of them in parallel to each other, very close to each other. So this distance is just for eye vision, simplify eye vision. Consider them very close to each other. So then that means that phase difference will be at the ends, because current, remember, is gradient of phase and vector potential. So current to be zero, there should be difference of phases at the end of these barbells. These are superconducting films on substrate, say. And then we can have them rather close to each other, so that if this theta 1 is not theta 1 prime behind it, Josephson tunneling can make them equal to each other. So this is Gedanken experiment. So for that, I am writing theta 1, theta 2, theta 1, theta 2. Okay, now suppose that this blue one, you can rotate pretty fast, so that like here, we are rotating it pretty fast, and then we stop in this position when this theta 2 now in here and theta 1 is there. So of course this is not very ideal, because during the rotation there will be some exchange between the phase values here. So it will not be clearly theta 2 and theta 1, but it will be close to that. In Gedanken case, we can do that. And if we will do that kind of motion and bring them close to each other, so that instead of dielectric layer, we will have very thin layer of vacuum between these barbell ends, then you have Josephson effect here and here. And the Josephson current is sine theta 2 minus theta 1. And here you have similar situation. And in this loop, you will have a current. In this loop, you will have double Josephson loop, you will have a current. So this means that your Carlis vector potential, with our help, was able to drive current here, which means that this is something which can indicate presence of of Carley's vector potential in the space. So so this was, of course, a Gedanken experiment, but and there are many additional questions one can ask, because we cannot rotate it faster than speed of light, and there is also finite time. It is related with Swichert modes and some other effects. So for these phases to keep their values, but as I said, roughly by order of magnitude, we have correct qualitative description of how vector potential is doing job here for us. And again, it is not because in superconductivity, when the phase is moving the current, it is, how to say, it is always rising questions, how this happens, how the electrons are starting to move, and these questions are not easy to answer, but this is what it is. So, and they are disputable, discussable, and in principle, all answers can be found. So now second Gedanken experiment. This time, we consider our initial layout. So we have only one strip, and angle, solid angle at which we see this strip is alpha. At the distance rho from the flux core. And what we measure here, the voltage. The leads, normal leads, usual voltage measurement circuit, but this L is superconductor. So again, we consider current expression, which is gauge invariant. So considering this and the properties of the solenoid, I wrote here. So what happens? We can calculate this integral ADL, and if it is short enough, we can approximate simply like this, and then obviously this value will be flux in the solenoid times solid angle, right? And solid angle will be this one. So I'm asking you to pay attention that we don't have any modulus of phi here. It is just flux, total flux, which is in it. This is important for this consideration, because it can be much bigger than modulus value, because modulus value should be restricted, right, by the phi naught. And here we can have million of phi, for example. But let's see what we should expect. So, and it is easy to see that we should expect flux, spikes of voltage if we will start cooling the system down from normal state to the superconducting state. So when we will do that, superconducting nucleation will start occurring in this superconducting strip. So when at time zero, when we just crossed the critical temperature by cooling, one can expect that current, there should be some spontaneously occurring currents, because gradient of theta is not A. A cannot determine the phase at a point, so different points will have different phases. So at the very beginning, there is no phase matching yet, and at the end, when formally it is infinitely a long time, we have no current now, and now it is complete phase matching. So during that, between this and these moments, there is some turbulence in the system. And in principle, we can detect some voltage difference at the ends. And it is interesting that we found that in the literature, this kind of topological or quantum, I would say, peculiarities have been predicted first for strings in cosmic domains, and then in superfluid helium, and then they were detected in condensed matter systems, in superconductors. So, so even without any vector potential, just when you have piece of superconductor making transition from normal state to superconducting state, you can see some voltage signals across the superconducting body. So it is interesting how this A vector, presence of A vector will affect because we can by hands change its flux from experiment to experiment and cool down and see what is going on in this superconducting lamella. So this is our second Gedanken experiment. And we decided to make some numerical estimates, which kind of voltage can we expect. And it is rather interesting what came out. So in ideal case, of course, so we probably in reality should reduce this by order of magnitude, maybe even 2 orders of magnitude. But any case, the arguments which I already discussed and tell us that we can expect during some short period of time some dephasing, and the time derivative of that will be voltage in accordance with Josephson-Anderson relation. Again, we are using theoretical units. Hc by 2e is equal to 1. So we should have that coefficient somewhere here. But any case, and then we can integrate this. When integrating gives some nice sum rule, which says that enveloped voltage is the value of the flux at solid angle of observation, which I showed you this alpha. So, and the time of duration when the equilibration of turbulence will take place is on picosecond scale. It is rather short in accordance with Ginzburg-Landau, time-dependent Ginzburg-Landau estimates. So, but that means that peak value is relatively high. So this is a peak value estimate, and it is, if I took 10 here instead of 10 picoseconds, and we have 1 million of phi naught in our solenoid, and solid angle is half, which means that we have half circles there, something like that. Then peak voltage is 300 microvolt per square root of hertz, so which is rather big value. And in principle it is detectable. So, but we obtained this very recently. We haven't yet been able to do anything with it. And again, this was Gedanken. And then the question, how Gedanken are Gedankens? So number one was definitely Gedanken. The second one has some probabilities, that feasibility that it will be possible to record. And moreover, it has some predecessors. Our predecessors already have recorded something, but without scalar, without Aronoff-Bohm potential. So, and probably about 1 millimeter in diameter solenoid can accommodate this amount of phi knots. So superconducting bar can be a thin film strip with this width, which is pretty doable. So this is in mind to try to do. But the most important corollary from these two Gedanken experiments was a different theoretical conclusion. Theoretical conclusion is telling us that indeed, if we will go to the fourth dimension and start considering stationary and non-equilibrium situations, we can have some observables which the vector potential is causing. So in which case, again, we can, as I said at the very beginning, we can consider there are different opinions in the community. Some say that A is not real physical field, and only E and H are real physical fields. And I think that that is a classical physicist's conclusion. Yes, in classical physics, A is not a real field. But in quantum case, nobody says that quantum field should be able to affect at a point because quantum physics is non-local inherently. So quasi-local effects, which fields of type of the vector, Carless vector potential, are, from my point of view, are also fields, but they should be considered as quantum fields, not mathematical tools. What is take out from our experiments, Gedanken experiments, that we need to seriously consider effects which happen in non-stationary, non-equilibrium cases. And now I would like to show you results which have been obtained years ago. And at that time, I wasn't sure that it is. I was afraid that something was computationally wrong. But now I am understanding, and my colleagues are in agreement with me that we need to consider this in very serious manner. So see what is happening. The strip which I showed you on the previous slide is a superconducting film. This is superconducting film. So, and vector potential is in parallel here, I mean Carless vector potential. So we consider, I will show you a little bit later the animation and the video of this behavior, but first let's consider slowly. So we have transition, initially it is in normal state, which is blue color. I am making some perturbation of superconductivity here by hands just to start computation from non-zero value. So, but system immediately goes to blue because it is from an initial state is normal state. And then superconducting state starts evolving. See, time is 0 here, time is 10 here. And at time 30, these are very short moments of time. About 1 unit is about 10 picoseconds. So you have complete superconducting state between normal banks. Normal banks here are blue. So you have stationary, steady superconducting state. And we have Aronoff-Bohm potential present there. So we don't have any visible signatures of it. So we have this state, which is prepared now. It is, and computer now can, at modeling, can insert current, which is going in parallel with Aronoff-Bohm potential along the surface of the film. So this is a current profile. So current goes up to some value, then steady value stays, and then current is switching off after, or vice versa. It's at time 50, it goes up, then at time 200 something, it goes down. So this is the current profile, which current we put through the film. And in one case, current moves in parallel with Aronoff-Bohm potential. In the second case, anti-parallel. So, what happens? As soon as this current starts moving, your superconducting film is attaining Abrikosa vortices. So we have here vortices of flux quanta. From one edge, you have vortices. From the other, you have anti-vortices. They move towards each other, annihilate, and disappear. And eventually, at the middle, you have some broken superconducting state. And at that time, pulse is over. we adjusted the duration so that at that point the pulse is over, and see what is the difference between two states, which I told you. Oh, this is, by the way, the phase dynamics, which you also will see video together with psi function dynamics. So this is when it is parallel. This is when it is anti-parallel. So beginning is, they are different a little bit at tau 10, then 30, and then 71, you see that difference became strong. And you will see how different is the final picture in the superconducting strips. So this is, yeah, I am done. So this is the difference. This is when it is parallel, when it is anti-parallel. In this case, we have resistive state. Here, resistance will be much, much smaller. So now let's see how this occurs in real life. Phase is bottom and the psi modulus is top. And parallel, anti-parallel. Pulse is gone. Picture is stopped. So this we think can be, so I have no time to repeat this, but I think the situation is clear. So, so this is the conclusion. So at some point, maybe even our Gedanken experiment number 2 will be experimentally realized, and this can have practical examples. It is not just, it is of course very interesting from the point of view of quantum science to find out if it is quasi-locally detectable, but it can have many applications, like you can have hidden Dirac strings in solids, like topological defects, which in principle, if we will be able to see, squids cannot see them because they should be inside of detecting loop of the squid. So that is impossible. We need to be able to see them while they are out of the coil, out of the input loop of the squid. So in this device, which I just described, can record them. Interestingly, A field, as I said, is going as 1 over radius, and then solid angle delivers another power, 1 over R2, but magnetic field is changing like 1 over R cube. So if this device will start working, it may have very important applications in practical science, including military. So that's why we hope that we will have some good stuff for our society. So this is it actually, and I would like to express gratitude to you for your attention, and to Yakir, to Daniele, Jeff, and Andrew, and his team for this nice conference. And I think this is not town, but really nice. Okay.
Maybe Marco can set up while we have some questions. Yes, Luke?
Yeah, so your relationship between the current and the potential, that's the London equation? Is that coming from the London equation?
Yeah, a couple of times I use it, yes.
Okay, I've
Mine is A plus gradient of theta.
I've normally seen that the London equation as a gauge fixed equation. You sort of choose a particular gauge, but you seem to be lifting that.
No, so gauging by London equation, if you will write without gradient of theta, that is gauge dependent, of course. So London, but London understood that there should be phase contribution, and Ginsburg and Landau in their theory, it explicitly minus A plus gradient of theta.
Interesting. I've never seen that.
Yeah, no, that is correct expression. I just didn't call Ginsburg Landau, I said London. Because I didn't involve psi square.
Another question while we're letting Marco set up. So Armin, as far as I understand, your main idea is to
It's not been what I thought.
is to basically go beyond just the integral of the vector potential to include also the electric potential as well. That this is the fourth time. So you have basically A0 dx as a tensor, right?
I am not explicitly including force potential, but the loops, which are four-dimensional loops, that is what is doing the trick, I think.
Yeah. So naively, I would look at it, I thought there would be no effect at all because there's no.
I would
There's no
also think
closed-
like that.
There's no field.
No, you need to look at these loops, Wilson loops, they are so complicated. And,
Okay, do you have a draft about this yet?
soon we are preparing with the student, so until May, we probably will have.
Okay, fantastic. All right, thank you. All right, so the last talk, but certainly not the least talk of our conference will be given by Marko Kosic, coming to us from Serbia. So Marco's been here for several months now, will be here to the end of the semester. He is a Fulbright scholar, and he'll tell us about some of the work we've been doing together on this super behavior and the quantum bouncer.
Thank you, Andrew. So this is a small excerpt of the result we have here. And I am completely aware of the irony that I will preach to the choir about super oscillations and super behavior, but I had to include it into presentation, out of completeness, so that we have some kind of complete story. So this is brief overview. I will just define and give some example of super oscillation effect. We will discuss what are the super phenomena. This is maybe less known concept. And then we will try to see interesting behavior in a very simple problem, quantum bouncer problem, which is analytically solvable. So we will use it, this at our advantage. But interesting stuff about him, except it is simple, that he has many generic features of more general class of quantum systems compared to the standard example of very well used and abused particle in a box, no interaction potential, or harmonic oscillator, which has very unique features. For example, that each classical trajectory inside oscillate with the same frequency. So this is something which is called isochronicity, and it is rather special property. General systems don't have this property. So then we will examine from geometrical standpoint this super behaving and super oscillatory effect, how we see it in wave function, in shape of wave function. And we will try to construct some super oscillatory functions and super behaving wave functions, particular for this system. So we will not use the canonical example with sine and cosines, which is very familiar, because in arbitrary settings, it's not necessarily that you have control over it. So if you excite your system, you naturally interact with eigenstates, so you should play with them. Okay, so let's start. So what would be super oscillations? So if you consider function f of n, which is written here in this very simple form, you can use binomial expansion and to show to yourself, to demonstrate that its Fourier expansion is finite and it can be thought as composed of waves, which each of them has wave vector belonging to the -1 to 1 interval. But if you take a limit n goes to infinity, you can easily show that it actually converges to exponential function with parameter a, which is larger than one, and in principle can be arbitrary. So we can put here less than one, which will not be interesting, because then we will have a function which is still in the confined into this spectral bound. And what we can see, and we can define local wave vector. The local wave vector would be actually derivative of our function. Well, basically, we need the definition which can retrieve this value A. So this is the idea behind it. And if you plot how it looks like, you see for different values of n, you see graph on your right. You see that in the central region, you can see wiggles which go faster than expected. So if you look at the interval -1 to 1, you see 5 or 6 wiggles. So we are not yet fully developed. So we need to expand order approximation to more than 40 in this particular case. And then we will see that in this particular range, we should have 10 wiggles. Okay, this is nice. Well, we can use it. Immediate application would be, for example, to beat diffraction limit. So to have a smaller point spread function, we can use it in imaging. But immediate idea is, does this have any physical significance beside that you have like one narrow peak? And there is very beautiful Gendenken experiment where Professor Aharonov, in collaboration with Michael Berry, considered the case when you have a resonator or a box, and inside of it you put a photon which has some finite energy, and then you engineer quantum state to be given by this function. And now notice that it moves. So it moves in this direction through the resonator, through the waveguide. But this waveguide, especially, it has opening here, close to the coordinate origin, and this opening has Gaussian transmission function. And it's not that difficult to show that this actually acts like kind of filter. So it allows super oscillatory part just to transmit out of it, and it will not allow other part of the function to go outside. So it seems that this strange wiggle has physical meaning, that it actually represents true photon, which can be engineered to be have energy of gamma ray, and you started to play with wave, which total energy is, for example, a red photon. So this is a nice example. There is much more to it than just wiggles, and it can have physical significance. And then we should think maybe about these local wave vectors, and it can be connected to the energy. Okay, this particular case is not that difficult to guess because it's free space, so a wave vector and energy are directly related. It's easy, no introduction, I mean, no contribution of potential. So next thing you should consider, and this is actually recent work.
Mark, would you please go back to the previous slide? I didn't get the z-axis is the length of the fiber, right?
X-axis is length. Z is empty space. So x-axis is waveguide, and opening is here, and this is normal direction. So this would be a pole moving inside of the plane. So waveguide is here.
Okay.
So
is it two? Okay.
Yes.
Okay, it's a one-dimensional waveguide. Okay.
Yeah. So opening is here, close to the coordinate origin, and this would be orthogonal. Maybe I confused, but this is propagation axis Z, but it moves, it radiates outside of this in the free space. Is it clear now? Yes.
What was the envelope that you used in the z direction for the pulse in the waveguide?
It has very complicated structure. You calculate it out of basically you apply this transmission function to this, and you get some in semi-classical regime. you get some combination of exponential function, Gaussian, sine, cosines. It's messy, so I didn't put it inside. But this is actual scattering amplitude, actually calculated from using this theory. This is actually a beautiful paper of Michael Berry, how to realize this physically. So we continue now to the super phenomena. Well, we see that we can think about connections of super oscillation with excess energy. And can we generalize this behavior? Well, Andrew will say yes, of course. It is his relatively recent paper. So what are super phenomena? So if you take arbitrary observable operator, you always can make measurement, and you say my preselected state is psi, and I will measure, for example, position, and I will get so-called weak value in this particular case, but it will depend naturally on the coordinate. And we can think about it as distribution of local values of this variable. So if you like to think in the terms of, for example, Bohmian mechanics, this would be value of this physical observer, those particles inside the field in fluid they actually have. So in case of velocity, it will be velocity, energy, or so on. So we can go on, make an extensive list, but we will focus in this talk only on energy. And super phenomena happens when this local value exceeds the bounds or naturally occurring in your system. What is really interesting here in case of harmonic oscillator, Andrew shows that this super behavior has a nice twist to it. So if you consider motion inside of harmonic potential well, and you fine tune the frequency, basically how strong you confine your particles, you can have very nice limit where each individual state has zero energy, but when you combine them together, you get a wave with finite energy. So this would be energy out of nothing. You see, we are getting close to creation, to create our universe, how to sell out of nothing. So this is very interesting result, and it actually very well behaved. You can see when we increase order of approximation, how we get really sinusoidal wave. Okay, this is very nice, and Andrew was able to prove this because there are very nice examples of relationship between Hermitian polynomials which appear when you try to play with the harmonic oscillator problems, and it is possible then to make this kind of expansion and to actually you can see this with increase of n, it converges to exponential function. This is very, very nice, but can we do this similar tricks in more general case? Because this not all special function has this extensive list of internal properties. So are those special cases? How we can generalize? Should we be able to find this kind of behavior in other systems? And what we also know, when you can create super oscillatory wave function or super behavior functions, how long it will persist. So there are interesting questions for practical aspect. How long they last? Can we do that? Or these are just like interesting phenomena, like singular cases and so on. So this was one of the motivation why we'll try to do this. And which system we should examine? So obvious idea was to examine quantum bouncer. So what would be a quantum bouncer? But basically it's analog of quantum analog of bouncing ball problem. So we have ball at the beginning, we let it drop down and then rebounces. And if we consider now what happens in the quantum case, well, now it's not that simple, but we have eigenstates when we should expand our position, our wave function in terms of that, and we can solve it analytically. So this is one interesting reason why this system is actually very rich. It's extremely simple, but very rich. For example, there is a proposal how you can use this very intricate features of this to devise quantum elevator, when basically when you interact with your particle, you can measure it, you can make it to jump, and then you can show that you can lift your platform with basically zero energy. And for example, in earlier work, this problem of bouncing ball on top of, for example, of loudspeaker was used to study nonlinear dynamics. It's very interesting stuff that you can make your ball jump very high. It was beautiful work done in research. So this system is extremely simple. We have an analytical solution. Some of you will probably gave them to your students as like home assignment, but this is actually very rich and you can find interesting behavior regardless of its simplicity. But what is interesting, this kind of chaotic stuff usually will not appear if you don't have this kind of isochronic behavior. And you will see that this is what will create unique structures we will meet inside. So this is the boring slide. We unfortunately must have some boring slides. So this is how you solve this kind of problem. You solve in classical case, classical equation of motion, and you have equivalent Schrödinger equation. You have boundary conditions where basically you have reflective surface, so nothing can go beyond x equals 0 coordinate, and we introduce convention about units so that we can rid of all h bars, m's, etc. You cannot have theoretical paper with units, so it is forbidden. So we then reduce this. This looks like area equation, and then of course we look at the books. Well, this classical problem is not difficult, but it's not trivial because you have periodic trajectory, but it's given with parabolas, but you don't have clear and closed solution like you have like sine and cosine. But this marginally complicated stuff, you can define this parabolic, periodic parabolic function. And in classical, in quantum case, you can reduce this to area equation, then expand your solution in terms of area function. This is well known. We will skip this. This is, you believe me that it is easy to do. Now let's, okay, we have some time delay. So what happens in one generic example? For example, imagine that you have neutron source here, and then you have collimator, and at the end of this collimator, you have prepared neutron, which is represented by Gaussian state. And what is nice about this, you can do these integrals, you can find this, how it looks like, and then you can calculate very accurately what happens with it afterwards. So this is an example of one experiment which is actually really done. So it is not true that we don't have a gravitational effect in quantum mechanics. Well, if you have this kind of bouncing neutron problem, this is everything due to the gravity. And what you see, well, your wave packet naturally expands. Now it part of wave function of wave packet hits the reflective with ideally reflective surface, then interfere. This is something very well known and very expected. But when you proceed further in time, then you see formation of this kind of patterns where we have probability density very large, well, close to this initial position, which is expected, but we have this kind of crazy splitting. So we have probability density high going downstairs. Okay, it's expected, but we have this, which is rather mysterious, jumping up. And same, it seems that this rebounces and then again refuses to go down, but again repeats and go up. And we have reappearance of our ball. This is approximately third rebounds. So this is expected, but then this dynamics repeats. So this is rather interesting and peculiar. And the idea is where this energy comes from, why this thing do this. So how to understand it? Is there any connection with this super behavior? So we try to investigate things, and what I should mention that to see this kind of effects, you usually need to have large eigenvalue expansion. So this is semi-classical like. If you have only two states in your eigen expansion, of course, you see nothing. You see like one hill of the first state and then other state, and they just make these quantum bits. But when you play with multiple states, you can get crazy patterns like this. So since this is semi-classical in nature, well, let's explore connections and what we can deduce from classical mechanics. This is family of classical trajectory. You solve your classical problem, and it is very nice. You recognize this kind of crazy lines immediately by your eye. So what are they? They are actually caustics. And in simple terms, what that means, if you take a look at this particular distribution of points, you can immediately notice that there are places when you have change in multiplicity of the points. So in this region here, because I bounded my variation of initial velocity, I have no trajectories hitting here. Now I have here region with every point hit by one trajectory. Here now I have two, and so on. What is interesting here, when you cross this kind of lines, multiplicity change by two. This is property of caustic lines, so it happens whenever you have envelope of your family. So think of this as abstract function family parameterized with initial velocity, and you can solve for caustics envelopes in this line, and you will get this. So this is nice. And why it's nice in quantum mechanics and why it's big? Well, you immediately notice this Jacobian appearing here, which is conditions to have classical envelopes, but this thing appears in semi-classical propagator and also in semi-classical wave function. So when this thing is zero, then your wave function becomes large. And we can now understand why we have this kind of behavior. And in principle, if I would allow infinite variation of initial velocity, which is allowed according to quantum mechanics, because my initial Gaussian wave packet, it's infinite when it's not zero for large values. Then I can make that this constant goes actually to infinity. It is unlikely, you need to wait for a long time, but there is nothing to prevent this to happen. Now we can understand global structure, now why we have such a behavior. So can we understand why we have this particular pattern and why this veggie thing appear in many places? Well, it turns out that it is canonical diffraction integral, which is called, or other people call it Peirce function, whoever studied the diffraction. And it is interesting that it appears all the time because according to Whitney theorem, caustics can be built only up from lines and this cusp thing, which has very simple mathematical formula, and you can basically decompose these very complicated diffraction patterns into this elementary one. And how it looks like, well, I really model caustics with this pattern. This is theoretical pattern, and you can see we matches very well with what we see in numerical calculations. So additional fringes here are from this initial rebounds. So basically here you explain everything by a superposition of one ray here and three rays here, but we have additional one from first rebounds. This is like local model, so we add it and it creates this additional fringes. But overall structure is actually determined by this Peirce function, and what is beautiful about it is very regular, very orderly. It has a lot of properties we can exploit. So for example, we know that close to classical caustics, there is constructive interference, which then systematically transforms into destructive interference. What is really interesting, a cool effect, that you can have minima here, which are outside, and which are explained by superposition of two evanescent waves with progressive wave. So this is a rather strange effect when you hear it for the first time. But evanescent wave can interfere with progressive wave, and where it is noticeable close to acoustics. Why? Because evanescent wave decay is very strong. So very close to this line, it is strong enough to affect progressive wave. And this is interesting fact. And what happens here, you have pairs of zeros, and you can see it if you, that this thing dominates. You can see if you examine the phase function of your pattern, you can see a lot of places where you have all colors meet, and this means that this actually is place which phase is not determined, I mean well defined, so it is phase singularity, and actually you can convince yourself that this is true minima, true zero of wave function. So okay, now we understand it. Now take a look at local energy. So what is local energy? You can define it in the same way as I showed it previously. You take your state, act on it by Hamiltonian, and then post-select by position and divide it by overlap. And what you get, that it has two parts. Real part is what you expect. This would be time derivative of your phase function, which is according to classical mechanics what we expect to see when we analyze energy. And we also have very interestingly imaginary part, which is logarithmic derivative of density, change of density. So you can think of both of them as kind of measure of a change of shape of your wave function, and it has physical significance. First one is actual energy of your bone particle living there, and other would be contribution, I mean, kind of binding energy. You must, if you want to push particles to be in this particular place and to have this density, you probably need to give some energy to it. And change of shape is actually captured by change in imaginary part of local energy, and there is good reasons to believe that this is universal, that it also happens for any. Actually, there is another paper of Andrew about it. So what is interesting here, that in this particular case, our local energy is close to bound. So maximal bound is actually 152, but in close to this dislocations, phase singularity, it can go up. Actually, it goes much higher than 200, but I need to cut this distribution, otherwise you cannot see anything. You will see one pixel which value 1000, and everything will be just murky and we could not see anything. So this is very close to maximal energy with some modulation. This imaginary part is very close to zero. This is also what we expect, a classical analogy, that the imaginary part of energy is actually zero. But they both jump close to this location. This is interesting result. Now we analyze it from the standpoint of quantum potential, which we know that quantum potential marks the regions where you expect super oscillations to happen, and it actually it turns out that it also works for super behavior, also for super energy. I see the Kai approves this result. This is what we expected to see. Again, I had to truncate this expression also for quantum potential with close to this region where we have dislocation. It goes to minus infinity, but there is very nice match, and zeros of quantum potential are actually those black lines. So you can see that blue regions corresponds to the places where we have super behavior. So, okay, this is something done by physics. We see that we have a lot of points where we have super behavior. It is connected to the singularities of the wave. This is nice, this is generic behavior. Now, immediate question, can we have more? We actually did nothing to it, we just calculated. Can we engineer a state which will have super behavior at a desired position? So how to try to answer this question? Well, you basically write down explicitly expression for local energy, and then you immediately see if you put this to be given, then it transforms into a linear system. And question is, can you solve it always? Or there are like special places when this will happen? Can you make it systematically whatever you want? Well, in order to this to be possible, this thing should converge to zero function. To be a zero function, each term in its expansion must be zero. And this actually gives you a linear system. And when you do mathematics, you end up with a system like this. And all those guys, P are polynomials, which you derive when you expand Airy functions into Taylor series. And what is nice about this is that because of Airy equation, we never need to consider higher order derivatives. We can reduce them always to the zeroth and first. This is why we get these polynomials. But what is really beautiful about it is that they have this particular structure. P1 is always 1, and P2 is always 0. But what is then beautiful that this system is always has zero determinant. This means that we can always solve this, regardless of initial position. This is rather nice result. It's not that expected because we see if we do nothing, basically we have generic features, only caustics and dislocations, and close to dislocation, we already knew that we will have super behavior. This is something already expected. But it seems that this same tricks works even if you want to be also in time. And one example how it looks like, well, you put arbitrary grid of points whenever you want. For simplicity, I took only 64 points. When I have 64 points, I have 64 conditions. So I basically can manipulate 64 states. I calculate this linear system, solve it. I know that it's singular. And then I basically need to find vector from the kernel, and it is given by singular value decomposition. Rather easy. Actually, I do this first, and I was puzzled why I have singular matrix all the time whenever I change the coordinates. Initially, I thought I was just lucky. Or this is actually numerics, you know? You're never sure. Is this like numerical zero, something below numerical junk, which is accuracy 10 to the minus 16, or it's real? And it turns out that this system has very nice properties. You can do it whenever you want. Now, we would like to go even further. So we are not pleased with these canonical examples, which are basically expansion of exponential function. And then you use definition of exponent to then in the limit reconstruct super behaving function. So can we do something just using elementary ingredients, Airy function? Why? Because in this particular system, whatever you do, you excite these eigenvalues here, eigenstates. You cannot, I mean, maybe you can, but it is probably experimentally very difficult to excite a Lagerbeer or beams or whatever beams you can manipulate in optics, which is naturally appearing when you create these kind of beams. In this particular case, task was to create superoscillatory states using only Airy functions and eigenstate in this particular problem. So, well, again, how to do it? Well, you just start from the beginning and you use integral representation of Airy function, and you disregard mathematical details. You swap the place of integral and sum, and you say, I will justify it later, like it's customary. And then you notice immediately if this expression, this exponential sum, can be made to be another exponential, then you can plug it back into definition of Airy function, and it will converge to this function, which is shifted. Now, why would this be super oscillatory? You can do mathematics, but what is nice that in this particular case, position is proportional to energy. So these characteristic shifts, which are given by the zeros of the Airy functions, actually are proportional to the energy. So this is the reason why when you shift your wave function, you can get super behavior. This is a feature which we use to our advantage. And when you do mathematics, now you have your friend, you recognize it from Andrew talks. It's not surprisingly that it appears all the time, our van der Monde determinant. And I was so pleased when I derived this. I said, this is breakthrough, new things. And then I discovered that there is a paper about this by Jeff and Yakir and now the general theory of how you construct this, and actually appears. So it is okay, not that breakthrough, but it is totally consistent and it appears naturally without trying to emulate their procedure to generate super oscillations. So this is very satisfactory result, although it's not first to derive this. This means that we are on the good track. So I don't like algebra too much. I like geometrical picture. So this is something to try to convince you why this should be always possible. Sorry, one caveat here. This approximation doesn't need to be exact. Why? If you take a look here, this is oscillatory integral because of this part here. And this approximation needs to hold close to the stationary point of this. And it can break down afterwards, we don't care, because dominant contribution, which will give Airy-like behavior, will come from the narrow region close to the stationary point of this integral. So this is nice thing. So basically, you don't need to solve this up to all possible orders. You can solve it for finite interval of eta values, and then you can get interesting behavior. So how this works? Well, let's examine what our exponential sums are doing, how they are looking, and what patterns they are creating. So this is one example, and this is mathematics known as mathematical curlicue. So what you do, you take sequence of exponential sums, and then you connect them with lines. So you start with the zeroth term, you have sum from 1 to 1, and then second you have 1 to 2, and you plot them as a point in complex plane, and you get this. So you can calculate it for many and use many terms, like in this particular case, we have 50,000 of them. But when you resum them and use Poisson resummation, you get something simple. So you can reduce it. It is mathematically up to infinity, but dominant contribution comes from example, in this particular case, 8 terms. This is a very nice result. And what our curlicue is doing when we change eta, it is actually rotating. So think of it as a circle on top of circle on top of circle. This is standard epicycles. Now change circles with spirals. But every spiral rotates. So it is not that crazy that you can manipulate lengths, which means that you add here coefficients to make this to be part of the circle. And then you can have this nice convergence. It is not crazy because each link rotates, and it will rotate rather quickly. So you can find this sweet spot where this derivation works. So this is very, very nice result. We have a lot to say about it, but it will take us too long. Now, one example how this finite approximation looks like when you try to calculate it, what it looks like when you have something, again, interesting, because all our wave functions must satisfy boundary condition that all of them are 0 here, and each of them has different spatial frequency, and our coefficients are unfortunately very small. You see, they are given expansion coefficients. We can calculate them in this particular case without van der Monde. We can solve this integral, and we can reconstruct our approximation superbehaving state. So it turns out that those guys are practically very small and grow very slowly. And then it turns out that you have accumulation probability density close to 0. So it corresponds to a ball which actually sits here, but it has density, it's because it is not stationary state. He cannot stay there. So it is kind of cannon. So it shoots up and then
rebounces back, but take a look at that coordinate which it reaches is 120, very fast. And when we expect distribution of local energy, and I am showing only real part of it, you can see that now, and we check this, of course, I had to truncate it in order to be able to see anything. Target maximal energy, in this particular case, I manipulated this alpha to be 5. So everything 5 is actually this, I hope that you can see red here. But in this region here, I hope that you can see clearly, and I checked it, believe me, please. We have stripes that are superoscillator. So instead of points, now we have stripes. We have bigger region that superoscillate, and when we increase order of approximation, we see that this fraction of superoscillatory region increases, and in this particular case, it is 1/3 of the points are super behaving. Okay, so this is all what I have shown prepared for this line, and I'm ready to answer any questions.
Hey, thank you, Marco. Questions? Bob?
What is the trick? I have a basketball. I drop it. I don't see this behavior. So, I mean, I'm in a different corner of parameter space, I assume. So, what parameters would allow somebody to actually see this behavior?
In classical mechanics.
Well, in reality.
In reality, this is.
We have only one thing.
In reality, you need to have narrow wave packet. So if it is narrow, so this additional Gaussian, if it is narrow in position, that it means that its Fourier transform, which will give us momentum representation, has variance which is large. So think of it, this is a proper way to understand this problem is to look at from the fast space perspective. So you can have trajectory which starts from this, but it has very large initial velocity. And if you have this, then you have trajectory going up and returning down. And if you have a cannon which systematically tries every possible elevation, you have series of shell trajectories. I'm afraid that in this time I'm using this word analysis, but my brain stopped. So if you, in classical settings, if you think where is the most probable position to find shell, it will be close to these curves. So, but each cannonball has velocity, and it is not forbidden to have large velocity. So this is the reason why you have. If you go here, unfortunately, I need too many trajectories to be able to visualize this nicely. But believe me, if you follow one, it goes up to the ceiling and then goes back. So energy is conserved, everything is fine, but still it is puzzling. It was puzzling for me. I said, this cannot be right, when I first saw this. This is unexpected because usually you don't think problem is interesting. You never analyze, for example, what happened in this particular problem for your students when number of eigenstate is large. Usually you will say, okay, for students, like 2 states is enough for you. Just show any function and I'm pleased. But it turns out that there is much more to this extremely simple problem.
Okay, other questions?
Thank you.
Other questions?
Comment.
Please.
So in fact, actually, this trajectory was observed in ultra cold neutrons. Yes, it was observed.
There is actually experiment which I propose to do to be done in large event.
Already been observed.
Which experiment?
It's in Grenoble down.
Exactly, yeah, the cold neutral.
And what did they observe?
No, they see like a little bit of wave packet goes like a little bit up.
It was a little bit up,
Yeah,
exactly.
It's there.
How come? Are you sure? Because I proposed this experiment and I'm waiting for
It was
results.
done.
You violated
told me
causality.
20 years ago. I mean, they do routinely these experiments.
Quantum bouncer to yeah. They have not seen the acoustics. They have explored.
No, the acoustic. No. The wave packet kind of goes a little bit up. First of all, they only have 4 against
Yes.
like or very few, like
Yes,
4 or 5.
yes. They explore this region here.
But they see this not the acoustic, but this piece of.
Yeah, they explore it because I proposed this experiment to be done to see this. Their idea was to study gravity. So idea is since neutron doesn't interact with anything, it can be very good probe for gravity constant and to create very sensitive. First, it is cool that you have gravity effects, quantum gravity effects, but to build very sensitive accelerometer, measures of acceleration of gravitational field to measure capital G. And it turns out that the precision in this interference region, which was their initial idea, was not sufficient. So what I proposed, and they like that idea, this is like quantum bouncer collaboration, like first experiment was 2008 or something like that, to try to measure acoustics, because when you change gamma, you don't want to measure slight shift in this dark fringe. You can change angle of this acoustic line. So it will be easier to find discrepancies from acoustic line going here compared to this one than it is to have extremely precise measurements of maximum and minimum in these interferences fringes and to deduce value of gravitational constant that way. Because we have other way to do it, and to be practical and to give us new knowledge, we must beat this limit. We must measure it with greater precision. Otherwise, it is pointless.
Well, Ibrahim, you had a question.
Yeah, so I would watch it with a different picture. I would say that, well, I can solve the Schrödinger equation in a linear potential. I will get Airy functions. This is a special case when I go with a Gaussian beam as an initial beam, right?
Exactly.
So, and I see from the spread of the wave function upon, let's say, time, that these, let's say, the width of these Airy functions, the initial beam is extremely small, such a way that is exciting almost all of those energy levels.
Exactly.
That's the reason that you will see such a situation.
Exactly.
So I will try to help what Bob wants to see. What happens when you change that, let's say, scales, let's say the sigma or whatever you want to call it, to be a little bit broader, right?
Yes.
So because that's not true for all sigmas. If you have to go with a specific sigma, then you will see that effect.
Exactly.
Do you have results for the smaller one?
Yes, but I don't have it here. I don't have it here. What happens, basically, this is a kind of blurring window. So if you increase it here, acoustic will remain the same, but all those features will now be averaged.
Yeah.
So when you increase it even further, what you see in this particular case, it is like kind of river going here, and contrast is not that large anymore because then you are averaging all this feature with this particular scale. And it's very large. Of course, everything is averaged here and you see nothing.
Yeah, and the beauty of this is that when you do the expansions, you will get the coefficients, right?
Yes.
Then you have the time dependence.
Yes.
It's still the same coefficients.
Exactly.
It's so wonderful. Yeah.
Exactly. Because whenever you try to do it numerically, here you are fine, here you are manageable, but then errors, you always kills your accuracy at the end.
But let me resum Marco's, one of his main conclusions or findings is that we have, and later on in the talk, we have situations where you add up a bunch of waves with energy between here and here, but you get a local energy up here,
Yeah.
almost everywhere.
Yeah.
That's the main finding.
Yeah, very interesting. Yeah.
Other questions?
This example.
Yeah. Show me your curly Q, Marco, because I just want to tell this little story because this is part of the fun of doing research is, we start working on this. he showed me these curlicues and I said, this is the most beautiful thing I've ever seen in my whole life. I just love it. I need to understand it. We started working on it. But one of the things he didn't mention is that there are these red lines that join the centers of like these little galaxies. It's like we're going to call this the jumping spirals. We have to call this the jumping spirals. And initially, Marco found this numerically, and he said, okay, we have a formula, but this right-hand side, we found that somehow there is this e to the I 2 pi, a pi over 2 n, or nu, that's missing. We can't find it. We can't find it. And we spent like a month looking for it. A month, or maybe 2 months. I think 2 months looking for this extra phase factor. And what happens, you see this u goes from 0 to n, and n is like 50,000, right? So n is u is huge. And so what we did is we just threw away this 1/4. It's u to the 2/3, u minus 1/4 on top of 50,000. But that 1/4 was the origin of this missing phase factor. So we have to keep this little tiny factor of 1/4. Otherwise, this very delicate pattern all falls apart. So it's an extremely subtle problem.
So what it means, this link should be rotated by p-half, this one by p-half, and so on. And difference is huge. And it is not obvious in the first glance why this 1/4 is important in the first place.
Yeah.
Andrew, when the first time I saw this, immediately rings a bell that it looked like Fresnel integral.
It's connected. It's connected.
Exactly.
Yeah, but this is for this area problem, right? This is something area zero.
So this is genetic behavior. This kind of spiraling will appear whatever you put here, as long this is exponential sum. And this is actually the reason why we are preparing probably a separate application. There is a lot of structure hidden here. So, for example, if you can make this curlicue to align and to extend back into long chain, it is connected what is called wave revival effect. So if, for example, think of this as a time, usually if time is 0, all those phase factors coming from energy are 0. So this is actually 1. So you have initial wave function. If you can do this, they are aligned, then again you will reconstruct original wave function. It is counterintuitive effect, which is very well demonstrated. It's called wave revival effect. And if you can make it to be this kind of wiggly, you can make to group them into groups of 4, which are synchronized, and then you have 4 copies of your wave packet, and so on.
Yeah, I think we're out of time, so let's thank Marco again for the talk.
Thank you. I have great fun.
Good. Can you unshare your slides? Because I need to share just a couple things about our activities. Oh. All right, so I'm happy then to just a moment. I have too many screens open.
Usually.
Just a moment.
I don't know. This is not the breath of mine. It's my
Okay.
Yeah. And zero the code for this it is not here. Email me. No, I have it. I have it.
Tell me what.
Yeah, I will.
Tell me exactly. I did not move any. I did not remove any.
Interesting.
Here we go.
Did not intentionally move any.
It was an appendix.
Okay.
Okay, so I'm happy to say that I love this meeting. Thank you for all being here. Thank you for giving great talks. I loved it. I hope you did too. So I'm happy to close it. Just a few housekeeping things. First, let's give a round of applause to Sarah and Melina, who did a wonderful job. Good job. If any of you would like a copy of my book and don't already have one, I'm happy to give you a copy as a thank you for coming and participating. We also have little swag bags with IQS stuff outside. Feel free to grab that. For the workshop, we're gonna kind of play it more by ear whenever you guys wanna go. Some people wanna go now, or some people wanna go grab a lunch and go, or go in an hour. We're just gonna try to coordinate rides. So we're gonna go down here to Crystal Cove, which is a very nice park. It's a state park near where I live in Laguna Beach. A little picture of it is there. So it's about half an hour drive. We're gonna drive down here. And we're gonna, for those that are kind of coming, some later, some now, we're gonna rendezvous at the Beachcomber Cafe in Crystal Cove. So it's right there on the beach. And we're gonna take a little walk down along the beach. And so if you wanna, sometimes people wanna go for a long walk or a short walk, we can kind of figure that out as we go. Luckily, we're expecting very beautiful weather. We have sunny, beautiful Southern California weather, low 70s, perfect. The weather did not disappoint, especially for the people coming from miserable climates.
That doesn't include Canada.
Yeah. Yes. So the Beachcomber Cafe will kind of be our rendezvous point whenever we want to go. In terms of parking, so there is a parking, here is the address, Beachcomber Parking at Los Trancos. In Newport Beach, and it's nice because you see they have a little parking lot up there, and there's a shuttle that will take you down into the historic. There's these cool little cottages, like historic cottages. You can look around and check out up there near before you. And so the shuttle will take you there. So that's the address for those that are driving. So who can drive here? So I have 4 of us. That's great. I can take 4 people. And who needs a ride? So, okay, good. So, John, you claimed some of these people. So where's Ibrahim?
So Vincenzo, Utaka, and let's see, who else was coming?
Utaka's going there?
And Marco is coming.
Okay, and Ibrahim, who are you taking?
Bob and Eddie, they are coming with me because they want to come a little bit later.
Okay, so who else needs a ride then? So Emily, you can come with me, and who else? Okay, Luke, you can come with me. That's good. And so then everyone's accounted for then. We don't need any Ubers. Perfect. Okay. And then if people want to go, yeah, so that's good. So find your buddy. Don't go get lost. And then good. And then I guess the other thing is that then we'll have dinner at my house. So we're gonna arrive around say 5:30, and dinner will be at 6. The only rule my wife has is do not bring sandy feet into our house. She will kill you if you do that. Luckily, we have a nice little hose on the side. So this is my house. And then if you go in down to the driveway, there's a little grassy area over here on the left side. There is a hose. You can hose your feet off, and we'll have towels there, and we'll have a very nice time. We'll have a nice dinner that I'm providing, or I should not say the Institute is providing for your entertainment and
Does she
pleasure.
have a sharp sword?
Oh, yeah, lightsaber. And that's the address. And so we should be able to either drive or take an Uber. So if you don't know my address, there it is, 2995 Alpine Way. And if anyone gets lost or needs help or has questions, that's my telephone number. You can call me or WhatsApp me. Yeah, Utaka WhatsApped me this morning, so I know I have you. I have your WhatsApp, but yeah. So just let me know if you have any questions or get lost or whatever. Okay. So thank you, everyone. Lunch is outside, and we'll see you at the beach.
Yeah. Yeah.
After lunch, we can go to the hotel.
You can go to your life.